organic sciences. It has been a pleasure for me to be here. My name is Mauricio Quimbaya, and I'm the principal investigator of Project One in this effort, and I will be the chair of this day. We appreciate the presence of special guests, researchers, and students from the institutions associated with the program and others from education, industrial, and government for accepting our invitation. Please keep in mind that some of the presentations that we will have today, some of them are going to be held in English and some others in Spanish. Today, we will start our day with the last keynote speaker. So for me, it's a pleasure to welcome Dr. Luis Berhot, who is a principal scientist leader at the Landscape Restoration Group and the Alliance Biodiversity and SEAD, based in Cali, Colombia. He works on the forestry and agricultural issues with a climate change focus. And he currently leads the Servir Amazonia initiative, bringing NASA satellites technology to Amazonian villages to help them address deforestation, drought, fire, and economic development. So, Dr. Luis, we are looking forward to hearing you. So, welcome to our symposium.
Thank you very much. Can everyone see my screen?
Yes, we can. We can now, Doctor.
It's come through? Okay, good. Very good. Okay, so today I'll be talking about a special report that was published last year, about a year ago now, from the Intergovernmental Panel on Climate Change. And the special report is on climate change and land. And I will talk today about the land-climate interface and hopefully be able to relate it to some of the issues that you are discussing here in the OMICS Symposium this week. Just to briefly walk through what an IPCC report is, the Intergovernmental Panel on Climate Change is a collaboration between policymakers and scientists. It's a UN organization. The special report on climate change and land was authored by 107 authors. 40% of the coordinating lead authors were female. 52% were from, just need to get something out. Okay, 52% were from developing countries, and this is a key objective of the IPCC was to, over the years, to broaden the author base and really get a more diversity in the viewpoints that are represented there. So 52 countries were represented, 53% of the authors were from developing countries. We reviewed over 7,000 scientific publications, and really the objective was to look at what is new since 2013, up until about the end of 2018. The report was published in 2019. We also went through a very rigorous review process. We received over 28,000 review comments. IPCC reports typically go through 2 sets of expert reviews, and experts need to apply to become reviewers, but it's open to the wider scientific community. You submit your curriculum vitae, and then you're invited to review. We also go through 2 government reviews, and so governments also nominate their own experts within to present their own feedback to the authors. And every single one of these review comments is read and addressed during the review process. Okay, so a special report like the one we prepared took 2 years. The broader assessment reports take 3 years to prepare. So it's quite an undertaking and quite an international effort. The scientists also engaged in this particular report with the IPBES, which is the biodiversity assessment, the UNCCD, and with the Food and Agriculture Organization of the United Nations to make sure that we were providing analysis and assessments based upon the most current information, but it was also consistent with what was happening in other assessment processes. So the long title is Climate Change and Land, an IPCC Special Report on Climate Change, Desertification, Land Degradation, Sustainable Land Management, Food Security, and Greenhouse Gas Fluxes in Terrestrial System. So it's a very long title, and it mixes a variety of concepts. But what I would like to point out, first of all, is that we really try to address 3 problem areas. And those problem areas are desertification, land degradation, and food security. We related all of these to greenhouse gas fluxes in terrestrial ecosystems. And we also addressed issues of sustainable land management, which is seen as the solution to a lot of these problems and to achieving progress in desertification, land degradation, and food security in ways that are sustainable for society. So the report outline was proposed at a scoping meeting that was held about 6 months or 8 months prior to the beginning of the report. And the outline that was adopted was the 7-chapter outline. The first chapter is provides the framing and context of the report. The second chapter presents land-climate interactions. So this is where a lot of the greenhouse gas information is dealt with. We have 3 chapters, each on one of the main problem areas. So a chapter on desertification, land degradation, and food security. We then have a 6th chapter that looks at the linkage between desertification, land degradation, food security, and the greenhouse gas fluxes. And this chapter tries to deal with synergies and trade-offs, and looking at particularly at integrated response options that can simultaneously address the problem areas and address the greenhouse gas flux issues. The 7th chapter is really sort of the most policy relevant chapter. It's a risk management chapter aimed at supporting decision-making in relation to sustainable development. So I think some of the broad-based conclusion of the report is that land is under growing human pressure because we see significant increases in degradation, in desertification, in food security issues coming from production problems. Land is part of the climate solution. Without dealing with the land-based emissions, we cannot achieve the objectives of the Paris Agreement, the 2 degrees C objective or the 1.5 degrees C objective. Land alone cannot solve climate change. So while many forums over the past several years have talked about land as a bridge to getting people to be able to do something with fossil fuels, we cannot solve the climate change problem unless we deal with the fossil fuel issues. However, if we do deal with the fossil fuel issues, that alone is not sufficient to get us to where we need to go. We must also deal with the land-related issues and the emissions associated with how we're using land today. So what I would like to do now is go through the summary that we prepared for policymakers, because I think what this does is it pulls out very nicely the key elements of science that are settled science and that present policy relevant information so that governments can undertake action. And so this is figure 1, and I'll go through it a little more detail, the different panels within figure 1, but this is a representation of land use and the observed climate change that we covered in this report. And first, we show how temperature has changed over the course of since 1850, since the beginning of the Industrial Revolution, up until 2018, which was the last set of data that we reviewed for this report. And we present this figure in terms of anomalies relative to a baseline, an 1850 to 1900 baseline for observed mean land surface air temperature and sea surface temperature. The dark line shows us the global change in the land plus ocean mean surface temperature. And you can see that it's achieved, we've already hit 1 degree C. So we're already halfway to the Paris Agreement's objective of limiting to 2 degrees C. But I think the important thing to understand is that land warms faster than the global average. And that's the gray line in this figure. It shows the change in surface temperature only over land. And you can see we are beyond the 1.5 degrees C target in temperature increase over land already today. And so this is where a lot of the stress is coming, because a lot of our economic activities really are focused on land. So I think this was an important insight to policymakers that they didn't really appreciate. That you know, even if we're talking about global averages, what's happening over land is much more severe than what the global average indicates is happening. The second panel looks at land-based greenhouse gas emissions. Overall, we estimate 23% of anthropogenic greenhouse gas emissions come from agriculture, forestry, and other land use. And so the line one in this graph shows the net change in emissions in CO2. Methane is line number 2, and nitrous oxide is line number 3. All of these are relative to a baseline, so you can see that we have a significant increase in all of these. But also we can see the non-CO2 greenhouse gases are rising much faster than the carbon dioxide. The carbon dioxide has been slightly decreasing or stable over the time period that we looked at, whereas these other two gases are increasing. And a lot of some of the major sources of these gases are really in agriculture. This is the representation of the global land area and global land use around to around 2015. The bar chart depicts a series of different land uses across the global ice-free land area. And the bars are ordered in a gradient of decreasing land use intensity from left to right. So we have irrigated cropland represents 2% of the land use, and non-irrigated cropland represents about 10% of the land surface. Intensive pastures represent about 2%. Used savannas and shrublands represent about 16%. So these are rangelands mostly. And then extensive pastures, and these are planted grasslands, are roughly 19% of the land area. So you can see that agriculture really takes up a large portion of the land area. These grazed grasslands are 37%, croplands are 12% of the land surface. Plantation forests are roughly 2% of the land surface area, and managed forests that are managed for timber make up about 20%. Then the ecosystems that with minimal human use make up around 28% of the land surface. That means almost 3/4 of the land surface is already appropriated for human use. This unused land or minimally used land is mostly forests and other land, the barren rock, but also some unforested ecosystems that are also have minimal use, like grasslands and wetlands, for example. And then we have 3 panels across the bottom of the figure. One looks at agricultural production, and that's here on the left. And we can see that inorganic nitrogen fertilizer use has increased over 800% since 1961. Cereal yields have increased 200% since 1961. Irrigation water volume has increased by 100%. And the total number of ruminant livestock is around 75% greater than what it was in 1961. So these are all some of the major drivers of what we're seeing in terms of greenhouse gas emissions from the land and intensification of land use. At the same time, if we look at how food demand and increasing production are linked to consumption changes, and that's the middle panel here, panel E, we can see that the population has risen about 150% since 1961. The prevalence of overweight and obese has increased significantly. Total calories per capita have also increased, although not at the same rate that population has increased. The prevalence of underweight has decreased, so that's actually a positive trend, a positive element with a negative trend, as the prevalence of underweight in the population has decreased. And then if we look at trends in desertification and land degradation in the third panel, land use change, land use intensification, and climate change have contributed to desertification and land degradation. We see the populations in areas that are experiencing increasing deforestation has increased almost 200% since 1961. Dryland areas in drought have increased slightly, and you see a lot of noise in this data, and that's actually the nature of drylands. There's a high coefficient of variation in rainfall in these landscapes. So we have years that are particularly drought affected and years that are not. And then the inland wetland extent, which is an important reservoir of water on landscapes, in particular in drylands, is decreasing since, I guess this one starts in 1970. We just don't have a record that goes back to 1961. But the inland wetland extent is decreasing. And I should point out, particularly for this conference, that perhaps Latin America or South America has the highest rate of wetland loss at the moment. And if we're looking at highland systems in Latin America, the loss of paramo and other highland wetland systems is really reducing resilience in these landscapes, particularly with respect to water flow regulation. So this is an important trend, and it's particularly important for this conference, I think. I want to go through a bit through the first table, the only table that we presented in the summary for policymakers, and this table summarizes net anthropogenic emissions due to agriculture, forestry, and other land use, and non-AFLU emissions. And there's a lot of numbers in this table. I don't want to go through them in detail, but I do want to pull out a couple of things. So let's start, first of all, looking on the left-hand side of the table and looking at total greenhouse gas emissions. FOLU in column A represents the forestry and other land use, and this is predominantly deforestation, and probably about 85 to 90% of deforestation is actually for the expansion of agriculture. So it's predominantly a CO2 story. The methane and nitrous oxide are small components of this. The total greenhouse gas emissions here is close to 6 gigatons of carbon per year. The second column, column B, shows what comes from agriculture, and note that this is predominantly a non-CO2 story. So it's methane makes up about 2/3, and nitrous oxide, well, a little less than 2/3, and nitrous oxide the other third. And it's roughly equivalent to what we're seeing in the carbon dioxide emissions from deforestation. So altogether, we have roughly 12 gigatons of CO2 coming from agriculture, forestry, and other land use. Now looking across the columns, we can see the agriculture, forestry, and other land use as a percent of total net anthropogenic greenhouse gas emissions, and it's roughly about 13% of carbon dioxide, but it's 44% of methane and 81% of nitrous oxide. So when we add this all up, greenhouse gas emissions from agriculture, forestry, and other land use make up 23% of the global emissions. The final thing that I want to point out is really the carbon dioxide story, and looking at what's coming from forestry and other land use emissions, and comparing that to what's happening in land that's not part of the agriculture, forestry, and other land use accounting. The natural response of land to human-induced environmental change is actually removing roughly 11 gigatons of carbon dioxide per year. So this is predominantly absorption on non-managed lands. It's due to the carbon dioxide fertilization effect. It's due to nitrogen deposition primarily. And this is a bit of, you can see this as a subsidy that we're getting from nature. So we're removing roughly 25% of global anthropogenic emissions every year in non-managed ecosystems. So the net land atmosphere flux from all lands is a removal of 6 gigatons of carbon dioxide, per year in these ecosystems across the globe. So this is an important element. We expect that as agricultural frontier continues to expand, we're going to see erosion of this natural response as less and less land is available to take it up. But also, as stress increases on these unmanaged lands, we expect to see a decrease in this removal, a decrease in this natural subsidy that we're currently getting from nature right now, that's buffering human activities' impact on the climate system. The second panel at this table looks at food systems. And again, what we've done is taken the emissions from land that I summarized in the first panel of this. So we have the 6.2, which is the non-CO2 greenhouse gases from crop and livestock, 4.8, which is the deforestation. When we look at what the supply chain energy emissions are and total that all up, we get a food system total emissions of about 14.8 gigatons. And this is 23 to 35% of total global emissions. So 23 to 35% of all of our emissions come from our food system, okay? Production, transport, processing, and disposal. So let me zoom in a little bit on what's happening with the individual gases, and in particular look at what's happening with methane. So methane increased slowly from the 1980s and up to about 2000. Its concentration stabilized in the atmosphere, and then the accumulation picked up again in about 2006, and we've had a continued increase in methane concentrations in the atmosphere. And one of the big questions that we've been dealing with in the scientific community that's working on this is why did we see the pause, and then what happened to move past the pause and begin to reaccumulate methane in the atmosphere. And so if we look at what's happening with the isotopes, the isotopic signature of methane, of atmospheric methane, between the mid-1980s up until about the late 1990s, we had an increase in the isotopic signature, and this indicated, I should say, a lightening of the signature as it became less and less negative, and this indicates an increasing fossil source over this period. During the time that the concentration stabilized in the atmosphere, the isotopic signature also stabilized, but then as the accumulation resumed after 2006, the isotopic signature declined. And this indicates a biogenic source. So we have an increased contribution of the biogenic source to the atmospheric methane accumulation. Initially, we thought this was related to fracking, particularly fracking in the United States, the extraction of natural gas in the United States. But the isotopic signature actually argues that this is either an increased wetland source, an increased rice source, or an increased livestock source should be driving the isotopic signature. So it's still an area of active investigation. We haven't completely nailed this down yet, but this is one area that we're trying to understand just what is happening. But what is clear is that the biogenic component of emissions today is more important than it was prior to 2000. And if we look at the agricultural, what components of the agricultural system are responsible for methane, you can see that the large part of it is really associated with enteric fermentation and rice. So enteric fermentation is digestion in ruminants, and so this is the major source of methane. What I've plotted here are 3 decades, so from the 1990s to 2000s and 2010 up until 2016, using 2 different global data sources. So using the Food and Agriculture Organization statistics, using the EDGAR database, and then comparing that with national greenhouse gas inventories. And we don't have the national greenhouse gas inventories segregated by source, but we do have the cumulative agriculture one. And the national greenhouse gas inventories agree very well with these other data sources. But the conclusion that we draw is that really enteric fermentation has been is the major source. Rice is another one. Manure management is part of it. All these sources are growing, but none of these sources seem to be growing enough to explain the change in what we're seeing in the atmospheric concentrations. Nitrous oxide, as I said, 81% of this comes from agriculture. It continues to increase linearly, and we see no abatement of this anytime soon. The primary source of this is nutrient management, particularly inorganic fertilizer, but also organic fertilizer and nitrogen fixation in the system. And so if we look at the major sources, going back again to these same databases, we can see it's fertilizer use in soils and manure management are the major sources of these. All of these are growing over the past 3 decades, and all of these need to be dealt with. We are working, and many groups are working on trying to mitigate these types of emissions, and there are approaches associated with precision agriculture, timing of nutrient management, better nutrient management that are being looked at. We looked at, in particular, the effect of land use change, and this is a meta-analysis that was conducted across the globe. And I think some conclusions that we can draw in croplands are that in unfertilized systems associated with land use change, we see an initial spike in the nitrous oxide emissions, and then a decrease below the initial rates. The 2 triangles on the left-hand side of the left panel show forest systems for comparison. The lower one shows average tropical forests, and the upper triangle shows wet forests. I'm sorry, not just tropical forests, average forests and average wet forests that are classified as being in particularly humid climates. And so we compare this with what we see in unfertilized systems. When the systems in croplands are fertilized, we tend to see an increase over time and a continued increase with continued application of fertilizer. So it's a non-linear response to fertilizer in this case. In pastures, we also see an initial spike associated with land use change, and over time we see a slow return to about ambient conditions that were existing in the forest prior to land use change. In figure 2, we looked at land related to risks related to human systems. And this is the burning embers diagram. And so I just want to spend a second to explain how to read a burning embers diagram. This is a typical diagram that's used in IPCC reports. The burning embers uses a color code to indicate the severity of risk. Purple indicates a very high probability of severe impacts and high risk. White indicates the risks are undetectable, and there's a gradation between them, between moderate, high, and up to very high. There is also, as you see on the right-hand side of this, usually associated with these, an indication of the confidence we have for a particular transition. So H indicates high, M for medium, and L for low confidence in this. And we define confidence in terms of how consistent research results are, how representative research results are across the globe or across the particular phenomenon that we're assessing, and how robust the conclusions are across the different studies. And so this is looking at risk to humans and ecosystems from change in land-based processes that are a result of climate change. So in this panel, you can see we've looked at dryland scarcity, soil erosion, vegetation loss, wildfire and damage, permafrost degradation, tropical crop yield decline, and food supply instabilities. And where we see the impact at the lowest temperature changes, keep in mind that the axis on the left-hand side is the global mean surface temperature change relative to the pre-industrial conditions. So we again have the 1.5 and the 2 degrees C targets of the Paris Agreement on this graph, but we also represent modeling experiences up to about 5 degrees C change in temperature. And what falls out of this graph is that the food supply instabilities, dryland water scarcity, and wildfire damage are perhaps and permafrost degradation are perhaps the most sensitive to temperature change. Soil erosion is much less sensitive to temperature change, and tropical crop yield decline is intermediate. It's sensitive, but not nearly as sensitive as some of these other elements. And so this is our attempt at trying to assess risk and then apportion risk. And you'll see in the lower part of this panel, the systems that we identify that are at risk in each one of these areas, whether it be the food system, livelihoods, value of land, human health, ecosystem health, and infrastructure. And so this is one of the approaches that we use to assessing risk management. The other one is to use what we call shared socioeconomic pathways. And so within the scenarios group in IPCC, we've defined 5 different socioeconomic pathways with representing current baseline and continued of current trends versus assumptions about population growth with low population growth, medium population growth, high population growth, and then different economic choices that society is likely to make with respect to decarbonization or continued fossil fuel intensity use. So here what I presented are just the shared socioeconomic pathway 1, which represents a world with low population growth, high income, reduced inequalities, food produced in low greenhouse gas systems, and effective land use regulation with high adaptive capacity. And compared that with SSP3, which has the opposite trends of high population growth, high greenhouse gas intensity. And to illustrate how risk changes based upon the types of choices that we make at the policy level with respect to desertification, land degradation, and food insecurity. So you can see that high population growth and continued fossil fuel intensity, continued socioeconomic inequalities leads to much higher risk world. It's perhaps a bit intuitive, but these are the ideas we want to make to policymakers is these are robust conclusions based upon deep analysis by multiple integrated ecosystem integrated assessment models that are combined biophysical socioeconomic models. We look at the potential contribution of the response options to mitigation adaptation, combining desertification and land degradation, enhance food security. And this panel tries to show the response options that can be implemented with or without, with limited or without any competition for land, including some that have the potential to reduce the demand for land. And so just to dig in a little bit on how to read this graph, blue shows positive trends, red shows negative trends, with the dark blue showing large positive trends, dark red showing large negative trends, and to show how we've defined these with respect to mitigation, adaptation, desertification, land degradation, and food security. And you can, this shows that, again, that we've tried to present messages to policymakers in gradations. We also indicate associated with this, again, high, medium, and low confidence. So where the science is robust, where the science is less robust. And we've also tried to assess what constitutes a high cost, a medium cost, and a low cost options. And just to zoom in a little bit on this, you can see we've covered areas related to response options related to ecosystems and ecosystem management, soils and soil management, forests, and agriculture. And tried to indicate where we have robust positive things that can be done, where these are low cost, where these are high cost. So for example, improved livestock management with respect to food security, we have low confidence in it, but it does have high potential, but it's also high cost, for example. Where we have some more intermediate confidence. So for agroforestry, for example, with respect to mitigation, we know agroforestry systems have more carbon, more biomass on the landscape. So we're fairly confident, much more confident in that response option from a mitigation perspective. We also know it provides adaptation options. It's being widely used at the moment for desertification control, for restoration of degraded lands. Its impact on food security, we're much less certain of, because you do have some trade-offs between the tree component and the crop component. And then we also look at demand side response options. So these are looking at reducing post-harvest loss, dietary change, reduced food waste, sustainable sourcing on the supply side, improved food processing and retailing, improved energy use in food systems, and what their potentials are. We also look at a couple of risk management types of options. So looking at livelihood diversification, management of urban sprawl, and risk sharing instruments. Again, indicating where we have no data on costs and where we have some data on costs. I want to jump off for just a second and show a little bit what some of these response options might look like. Drawing on some CIOT research, and this I think maybe speaks a little bit to the subject of this conference on the omics. And I'm not an omics person. I'm not a genomics person. I'm really a greenhouse gas person. But we work a lot with our breeders, and in particular, we're working on Brachiaria grass. Brachiaria is probably the most widely planted crop in the world. There's 99 million hectares just in Brazil that are planted. It's also widely planted in Colombia and other countries. Over half of it is Brachiaria brisanta. Other species make up another 50%. Decumbens, Rusensis, humidicola are also planted widely. These are stoloniferous. They're rustic, well adapted to low fertility environments. They tolerate seasonal inundation. We have several CIOT cultivars that are available. And more importantly for this talk, there is some potential for these grasses to inhibit nitrification. And this has a relationship to what we were talking about earlier with respect to nitrous oxide emissions. So our breeding folks are looking at hybrids of Brachyuria decumbens and brisanta, excuse me, and looking at trying to generate hybrids that have the positive attributes of both of these species. And what I'm trying to look at here is the ability of these cultivars, not cultivars, these hybrids, to suppress nitrification. So BNI refers to biological nitrification inhibition, and we see that some of the cultivars, or the varieties that we have developed, have very high BNI capacity. Some have intermediate, and several have low. And so this is based upon an evaluation of 40 germplasm accessions using acid soils in pots over 180 days, and their nitrification inhibition potential. These are the results that were published in PNAS a few years ago. The mechanism is the root exudation of brachyaltone, which is a nitrification inhibitor. You see in the lower left-hand panel, we have ammonium oxidation rate in the soil, and you can see that there's a wide variation in the different varieties that we have. So we have what we see in bare soil, what we see in soybean. PM is panicum maximum. The BHM is the Brachyuria hybrid called mulatto. And then we have the BH 679, which is humidicola, one of the humidicola varieties, and the 16888 is another humidicola. If we look at the nitrification populations in these different soils, you can see a significant suppression of the populations. And in the lower right-hand side of this panel, you can see the impact of this on cumulative nitrous oxide emissions in a field assay that we ran in these different different varieties. So through breeding and proper genetic manipulation, we actually can achieve some nitrous oxide emissions reductions. We don't quite get to zero, but we do get a significant reduction. And these types of technologies are what we're talking about when we talk about response options associated with perhaps intensification of agriculture, but diminishing the negative environmental impact. So I'd like to go back to the report a little bit and look again at the third figure, which shows the potential global contribution of response options to mitigation, adaptation, combating desertification and land degradation, while enhancing food security. And in this panel, we show the response options that rely on additional land use change that could have an impact across 3 or more of the land challenges with significant implementation context. So to zoom in, bioenergy and bioenergy carbon capture and storage is widely touted as a technological breakthrough that will help us get to where we need to go to continue to use fossil fuels, but then also to transform the energy system to a more sustainable condition. So if we've done here is we've looked at sort of high level of implementation in the top part of this panel and best practice implementation, and these are all nicely defined in the report. But the high level use of bioenergy has a very high significant mitigation potential. But you see the red on the food security, there's a very significant land use trade-off here. As more and more land gets used to produce bioenergy, you have less and less land available for crops, and you get an economic trade-off there. The cost can go from low to very high, depending upon how it's implemented and where it's implemented. But I think it's important. One of the important things is that we highlighted this food security issue. We also show in the second part of this that there is a middle ground that can significantly reduce the food, but not completely eliminate the food security risk. We don't get as near the mitigation, adaptation, desertification, or land degradation benefits. So really the scale and the nature of deployment of this technology is going to determine the impacts, and there's a real trade-off here that policymakers need to be aware of if they're going to go down this road. If we look about reforestation and forest restoration, all of these have high mitigation potentials if implemented at a high level, potentially high adaptation, desertification, land degradation, but there's maybe a bit of a food security trade-off. Implementing this land restoration, and we took this to mean ecosystem restoration, so returning ecosystems to more or less their natural state, means taking some land out of production, and without proper intensification on land that remains in production, we could get a food security trade-off there. Best practice, looking at doing this, balancing this food security risk, we actually can get to moderate contributions of all of these in all of these areas, including improved food security if done properly. And that includes soil restoration. This is looking at afforestation. Again, we have strong mitigation, adaptation through modification of the water cycle, through reduction of erosion, through desertification, improvement of land degradation issues, but a very strong food security trade-off if implemented at very high levels. And again, that decreases if we go to a best practice type of approach on this. And then finally, biochar addition to soils also has a high mitigation potential, but there's also some food security trade-offs, and that's associated, depends upon where you source your biochar from, and also how much land you actually have to dedicate in order to implement that at very high levels to production of this, which could create some competition for land. And again, a best practice approach to things could actually help even out some of these risks. Maybe not give as strong a benefit, but maybe also not create the negative trade-offs. And then the fourth panel looks at pathways of linking socioeconomic development, mitigation, and responses in land. And the socioeconomic development and land management influence the evolution of the land system, including the relative amount of land allocated to different land uses. Okay, and so we use the integrated assessment models and 3 alternative pathways using the SSP 1, 2, and 5. So 1 being the shared socioeconomic pathway 1, representing current low population growth, but strong adaptation, strong improvement of inequality. 2 is society as well as technological development flows. We see an increase in demand for land mitigation. And then resource intensive is represented by number 5. So you can sort of see this as, sustainability focus, middle of the road, and then resource intensification between 1, 2, and 5 that we present here. And so we look at the different representative concentration pathways for this, and this is the greenhouse gas concentration trajectory that's adopted in the last IPCC assessment report. 4 pathways are selected for climate modeling, and that describe the possible future climate futures. So the RCP 1.6, 2.3, 6.0, and 8.5 actually refer to the warming in watts per square meter. These are the units that we often use. These are units of energy per square meter. They correspond to an approximate temperature change increase in 2100 of 1.5, 2.4, 3.0, and 4.9 degrees C. We've modeled, the modeling community has produced the results of what the likely carbon dioxide concentration looks like. So to get to 1.5, we shouldn't be going above 490. To get to 2.3, it's 650, on up to over 1,300 parts per million. And then the pathway to get there is also important. So the 1.6 pathway has a peak and decline approach to things, because we're already committed to probably overshoot on if we're trying to hit a 1.5 degree target. The other 2 represent stabilization, and then the 8.5 represents a continuously rising trend. And so what we see is if we look at the sustainability focused from land, we look at changes in land, we will see in the sustainable one, we have an increase in forest land, we have a decrease in pasture land, a decrease in cropland in this. We have an increase in bioenergy cropland, and then the natural land remains relatively constant. Okay, in the middle of the road scenario, we have a slight decrease, a much less decrease in cropland, a similar decrease in pasture land, an increase in biocarbon, bioenergy cropland, continued increase in forest land, and then a more significant decrease in natural land than in the SSP1. And then the third one, we're looking at the resource intensive pathway. So we have a significant decrease in cropland, a even deeper decrease in pasture land. The bioenergy goes up significantly. This is a very intensive bioenergy system. The forest land increases, and then the natural land decreases and then recovers a bit over the course of the pathway. And so these scenarios are trying to help policymakers analyze, if we make different choices, what is the likely impact of land use as we make different economic choices? Because very often land use is driven by these higher level decisions that are made at national level and negotiated at international levels. But these things actually play out in real ways in real places across the globe and in ways that are actually predictable. And then so linking the socioeconomic development and mitigation responses to land, we have a number of ways of doing that in the second panel of the figure, and this looks at the land use change in land cover in the different SSPs. Again, trying to look at the change in natural land, change in bioenergy and cropland from 2010, change in cropland, change in forest, and change in pasture. And so this is putting these actually into numbers globally in 2050 and in 2100. So again, that it provides some indication of what the different models predict with respect to different development pathways that the countries will choose. And this is aggregated at the global scale. Again, we have it for SSP3 and SSP5. I don't think it's worth getting into the individual numbers here. I think that the graphs that I showed at the beginning really lay this out nicely. But I think the point is that we do have choices ahead of us. Some of these choices are actually not feasible. So we in the socioeconomic pathway 3, if we wanted to stay within 1.5, 1.9, or 2.6, the representative contributed pathways, keep in mind 1.9 represented a 1.5 degree change in temperature, which is one of the Paris Agreement targets. The 2.6 had the 2 degree target, so that was also one of the Paris Agreement. Within this SSP3, neither of those targets are actually feasible. So we not all options are feasible for achieving all of the targets. And finally, the land use cover and land use change in the different models summarized. We see that we can actually make global predictions across the different pathways to indicate where society wants to go, or to help society make choices about how they want to allocate land and what they want their landscapes to look like in 30 years and in 70 years. So I'm going to stop there, and I'd be happy to answer any questions on this, and hopefully this is related somewhat to the discussion that you'll be having today. But I really want to thank the organizers of this, and Andres in particular, for the invitation. It's been a pleasure to be able to present this to you, and I hope you find this report useful. Thank you very much.
So thank you very much, Dr. Bershot, for your talk. It was a really, really nice talk. So we have some time for some questions from the audience. So indeed, we have some questions. So Nicholas is asking if, do you think that this year's data of greenhouse fluxes might be influenced by the coronavirus pandemic? And if it's those data are influenced by the pandemic, which is the amount of this influence, if we can measure it?
So these data are very closely aligned with economic activity. So to the extent that the coronavirus has, and this is documented, it has significantly had an impact on economic activity. We are seeing decreased emissions of carbon dioxide associated with slowdown in industry, slowdown in production. Again, the real slowdown started in March, and countries will only begin submitting their data to the UN at the beginning of next year. So we will start to see these data in national reports as they come out, I guess about the middle of next year. But I would certainly expect to see a decrease in CO2 emissions from fossil fuel sources, perhaps a decrease in nitrous oxide from fertilizer application, and perhaps we'll see with the methane. That could go either way, depending upon what's happened with livestock herds across the tropics and across and I say the tropics because it's largely the growth in livestock herds across the tropics that appears to be driving this at the moment, particularly China, India. So I expect to see a significant impact on greenhouse gas accumulations, and we'll have those data. I can't say what those are right now, but we'll have those data early next year.
Okay, thank you very much. Doctor, you said that 23% of the gas fluxes are coming from agriculture and 44% of methane production. But for food security, we need to produce better and we need to produce more. It is possible to reconcile agricultural practices with climate change mitigation, and what can we do as a developing country for doing this?
So I think there are a number of things that can be done, and I think all countries have a role to play in this. I mean, the data when I did take a step out of the report, I showed you actually a very good example of what can be done about nitrous oxide in pastures, in tropical pastures. Brachiaria is essentially a tropical grass. These types of approaches can be developed. I think there's a lot that can be done around diet management and intensification of meat production. So shortening the time it takes to get a product to market, through breeding, through better nutrition. I think we can do an awful lot there. There's a lot of unproductive or low productive livestock production systems. And so sustainable intensification of these, reducing the greenhouse gas intensity of production is certainly going to be a key to that. I think there's also a shift, and we're actually seeing it happen globally in the types of meat that are being consumed. The demand for beef has been fairly constant, and the production of beef has been fairly constant over the past 20 years, whereas the production of poultry and pork has significantly increased. A lot of this is driven by what's happening in Asia, and there's a preference for pork and poultry in Asia over beef. So I think we're also, there's dietary shifts that can happen, and shifting from ruminants to monogastrics is certainly one element in that.
Okay, thank you very much. Doctor, this is a very detailed scientific report for world leaders, for governments, for policymakers. How receptive are they to this kind of information? And I don't know, especially for the Colombian government, how receptive is the Colombian government for this kind of information?
Yeah. So keep in mind that this report is actually, it comes from the United Nations. So it's requested by governments, and governments sit down with scientists at the beginning and develop an outline. They want to know this, they want to know that, they want to know all of these. They ask the questions, and they ask the scientists, please provide us answers to these questions. So this is a demand-driven process. We also sit down at the end, once we've reviewed all the literature, we sit down again with the governments, and we write a summary for policymakers. And we, the scientists, we first get together and write a draft of what we think is important for the policymakers. Then we sit down with the policymakers and say, no, this doesn't really help us. We need to know this. We need to can you turn the argument around and explain it in these terms or that term? These are the types of indicators that we're following. So it really is a dynamic process between policymakers and scientists to make sure that the report does meet the needs. Now, different countries participate with different levels of intensity. But Colombia was present and Colombia was active in the discussion. I think even despite the change in government, I think the technical people in the ministries still think that this information is important. They're trying to act on these. We've seen, taking the example of Colombia, with the peace process, there was a real spike in deforestation in the Amazon for the first 2 years following the signature of the accord, and then a subsequent decrease in those emissions and in the burning, in the deforestation, as the government got control over the areas and began exerting some control. So I think there is a lot of demand and responsiveness on the part of governments and specifically Colombian government to this information. I think the Colombian government does try and be evidence-based and base their policy on science. So I think they want to know this information.
Okay, thank you very much. So there is hope. So finally, we have time for, there is hope. So finally, we have one last question from Andres Jaramillo, who is the scientific director of the program. So I open the mic and the video for Andres.
Yes.
Thank you, Mauricio. Hi, Louis. How are you?
Very well, Andres. How are you?
Good, good. Terrific talk. Thank you very much.
Yeah, no, thank you.
So it's not only a terrific talk, but a terrifying scenario moving forward. I mean, I think it's worrisome to see that even if you control one variable, a lot of other variables are really not controllable.
Yes.
So for OMICAS, one of the efforts that we're trying to pursue is really to look at accurate ways to measure greenhouse gases. And methods that don't rely on, expensive instruments like chromatography and spectroscopy and whatnot. The question is, if you were to choose between, CH4, N2O, or CO2 as a high impact greenhouse gas that could be controlled through breeding techniques, it seems that N2O continues to increase linearly. It seems that CO2 agriculture has an impact, but there's other sources of CO2 out there that are very hard to control. So if we focus, for example, on N2O and on breeding techniques, do you think creating or developing technology that would allow the small agricultural, owner to actually measure these emissions and certify its emissions with a high resolution or accurate measurement of N2O emissions, would that be useful? I mean, we're trying to think, we're developing sensors for biomarkers, and one of the things we're looking at specifically is really methane emission, but I think methane might not be the key element here, and it might be N2O. So that's a question more related to the technology side. What would help more the breeder, either measuring accurately in extensive lands N2O emissions or CO2 emissions from agriculture?
I think there are probably easier things and still meaningful things to measure that are not necessarily the gases themselves. So, for example, I could see that there are microchip technologies looking at some of the genetic markers for nitrification or nitrification inhibition, right?
But that requires invasive techniques and requires destructive measurements. So we're trying to think of a way of measuring without affecting the organic, the biological organism.
That's right. I think what you're going to be able to measure is what people are actually doing at large scale, and you're going to need sort of multi-tiered types of measurements. So measuring how many people are using an improved variety that perhaps inhibits nitrification.
Sure.
Then targeted measurement in the field under field conditions of just how effective is that nitrification inhibition. And then in a few cases, you may need some of the expensive measurements based on gas chromatography to validate your measurements of decreased nitrification or of nitrification inhibition increases and the output of nitrous oxide. it seems to me that, if you look at some of the, I see some of these assays and these soil microchip types of approaches. You take a small soil sample, you do some extraction, maybe some PCR amplification, and then you can look at what's happening in your environment. There's an awful lot going on with biosensing and genetic analysis in natural environments to determine changes in microbial community function and things like that. So those types of things, I think, would maybe help make things a bit easier.
Okay. Well, we were more inclined into providing new tools for the breeder. We think that the current scheme or strategy of actually using static chambers on site in the field is very cumbersome. It's very expensive. You need to collect the samples manually, and you need to do it periodically. So it's expensive, and it's not the ideal way of doing it. So we're trying to provide IoT devices that would be placed in land and left until the crop continues throughout its maturation process until the end. Mm-hmm. And for us to have real-time data fed from the emissions. It's not easy because these are volatile organic compounds that are very, it's traces that we're looking at.
That's right.
So it's not an easy task.
Yeah. As somebody who spent his career making the chamber measurements, another method would really be welcome. Yeah, you're right. It's cumbersome. Getting something that's representative is a real pain. Sure. It's difficult. Working in isolated places or faraway places, is difficult. You always have to deal with sample transport, sample integrity. It's not ideal. I think we've done as good as we can with that. But new technologies and new approaches to this would really be welcome.
Okay. Well, again, thank you very much, Louis. Excellent talk. I'll try to digest every detail today in the afternoon if and I might ask you some additional questions and perhaps try to meet at some point at CIET.
Yes, I'll be very happy to do that. Yeah.
And again, appreciating your time for this.
Yeah, no, I really appreciate it. I'm going to listen to a couple more of the presentations. So
great, fantastic.
Yeah,
good to have you.
Thanks so much. Appreciate it.
Thank you, Mauricio.
Okay, thank you very much. So let's move on to our next speaker, who is Manuel Camilo Valencia, who is an agronomist and is currently doing a PhD in agricultural sciences. He has expertise in the analysis of spatial and temporal variability of chemical properties in soils in the Department of Meta here in Colombia. And now he's currently working in the analysis of emission of greenhouse gases, mainly N2O in sugarcane crops here in the Cauca Valley. So we're really looking forward to hearing you, Manuel. So you can start.
Buenos días. Mi nombre es Manuel Camilo Valencia Molina. Hoy vamos a hacer una presentación acerca de las emisiones de óxido nitroso en suelos cultivados con caña de azúcar en el valle del río Cauca. En el desarrollo de esta investigación hemos contado también con la participación directa de Catalina Trujillo, Sandra Patricia Loaiza y Brian Moner. Ellos hacen parte de algunas de las instituciones aliadas en el desarrollo o en la ejecución del programa OMICAS. La presentación la hemos dividido en tres componentes. El primero es una pequeña introducción para dar de cierta manera un contexto del tema que vamos a desarrollar. La segunda es un recuento de algunos materiales y métodos. Y la tercera es la presentación de algunos resultados obtenidos en campo. A manera de introducción, nosotros queríamos empezar por aclarar cuál era la relevancia del óxido nitroso. Resulta que el óxido nitroso es un gas de efecto invernadero, hace parte de los tres principales gases de efecto invernadero generados en la actividad agropecuaria, que son dióxido de carbono, metano y óxido nitroso. Sin embargo, este tiene a pesar de que es de los tres gases es el que se genera en menor volumen, tiene unas características físico-químicas que le dan una cierta relevancia en comparación a los demás. Lo primero es que es una molécula que tiene la capacidad de absorber aproximadamente 310 veces mayor radiación infrarroja en comparación con la molécula de referencia, que para efectos de estos análisis es el dióxido de carbono. Esto es debido a una característica particular en la vibración molecular, ya que la molécula de óxido nitroso es una molécula que no es simétrica. La diferencia del dióxido de carbono, en el cual el carbono es el centro de la molécula y en los dos extremos tiene un átomo de oxígeno. En el caso particular del óxido nitroso, son dos moléculas, dos átomos de nitrógeno unidos a un átomo de oxígeno. Y el núcleo o el centro de la molécula es uno de los átomos de nitrógeno. Esto genera una condición de mayor vibración molecular, con unas longitudes de onda y unas magnitudes mucho mayores que le permiten absorber mayor radiación. La segunda característica es que tiene la capacidad de degradar el ozono estratosférico en la atmósfera, porque puede reaccionar o tiene la capacidad de reaccionar con el oxígeno monoatómico que está presente en la estratosfera. ¿Qué sucede? Que el ozono está en constante fotólisis y síntesis, lo cual permite que haya una molécula de tres oxígenos que generalmente va liberando un oxígeno y vuelve y lo asimila, libera y asimila. De tal manera que cuando estas reacciones se dan, en particular cuando el ozono, por efecto de la radiación, libera uno de sus átomos de oxígeno, si está en presencia de una molécula de óxido nitroso, tiene la capacidad de reaccionar y generar una nueva molécula de oxígeno diatómico y nitrógeno diatómico también. Desde el punto de vista ambiental, esto no genera mayores riesgos, porque este oxígeno diatómico vuelve a estar o queda ahí en la estratosfera y tiene la posibilidad de reaccionar con otros oxígenos monoatómicos y volver a formar moléculas de ozono. Y el nitrógeno diatómico pues está libre en la atmósfera y no genera el efecto sobre el calentamiento o su implicación desde el punto de vista del calentamiento global. Sin embargo, hay una segunda posible reacción, y es que cuando las dos moléculas, tanto la de ozono como la de óxido nitroso, tienen la incidencia de la radiación, se liberan un átomo de oxígeno como en la reacción anterior, y en la de óxido nitroso ya se libera uno de los átomos de nitrógeno, de tal manera que como producto obtenemos dos moléculas de óxido nítrico. Este óxido nítrico sí no es un poco más estable y no libera fácilmente este oxígeno para poder continuar con el proceso de la lisis del ozono. ¿Qué sucede? Que además es un elemento o es un compuesto que es potencialmente precursor de lluvia ácida, así como los otros, o como algunos otros óxidos de nitrógeno que se pueden generar o que pueden llegar a la atmósfera. La tercera característica particular de este elemento es que tiene una vida útil, o tiene la capacidad de estar estable en la atmósfera en un periodo hasta por 114 años aproximadamente. Es decir, que una vez llega a la atmósfera va a tener un periodo de tiempo suficiente para buscar la posibilidad de reaccionar con ese oxígeno monoatómico que podamos tener allá. Y otra cuestión de la relevancia, ya un poco más en función de la emisión del óxido nitroso como tal, es que el 27% de las emisiones globales de óxido nitroso provienen o son de origen antropogénico. ¿Qué quiere decir? Que son generadas por la actividad humana. Y de ese 27%, el 80% corresponde a emisiones generadas por el uso ineficiente de fertilizantes nitrogenados. En ese sentido, nosotros vemos que ya este problema de la emisión de óxido nitroso está estrechamente ligado al uso de estos fertilizantes nitrogenados. La siguiente aclaración, o el siguiente contexto que queríamos ampliar era el tema de la producción de caña de azúcar en el Valle del Río Cauca. Para muchos es claro, es evidente, es la zona del país donde se concentra la mayor producción de caña a nivel industrial en Colombia, ¿sí? Partiendo del hecho de que estamos en la región del Valle del Cauca. El Valle del Río Cauca es un valle interandino que está entre las cordilleras central y occidental, y pues están en la parte central de Colombia en términos de una orientación en hemisferio norte, hemisferio sur. En un sentido vertical, el Valle del Cauca está sobre el eje central. ¿Qué sucede? Que estamos en unas condiciones tropicales donde tenemos días de 12 horas, o sea, luz solar 12 horas al día durante todos los días del año. Y aparte de eso tenemos unas condiciones de temperatura y unas condiciones de temperatura un poco más constantes a las regiones con climas subtropicales o las zonas polares. Entonces, en ese sentido, estamos en un escenario en el que Colombia durante 2019 registró aproximadamente 500.100 hectáreas de caña de azúcar, de las cuales aproximadamente el 50% corresponden a producción de caña de azúcar en el Valle del Río Cauca. Esta producción o el desarrollo de este cultivo en esta región se caracteriza porque su el principal uso es la agroindustria, tanto de azúcares, alcoholes agroindustria de alcoholes y azúcares principalmente. Entonces esta producción está desarrollada bajo un nivel, un modelo altamente tecnificado con una producción intensiva, en la cual se recomiendan en promedio aplicaciones de más de 100 kilogramos por hectárea. Sin embargo, acá hay una situación, y es que culturalmente algunos productores deciden hacer aplicaciones de dosis mucho más altas sin tener en cuenta parámetros o las recomendaciones técnicas. Es decir, que van bajo la premisa de que es mejor que sobre y no que falte. Y si bien desde el punto de vista productivo eso les puede garantizar o les puede asegurar algunos aspectos en términos de producción, desde el punto de vista ambiental está generando un riesgo y está afectando la sostenibilidad productiva, porque no solo, en este caso nosotros estamos analizando el tema de las emisiones de óxido nitroso. Sin embargo, el uso excesivo de fertilizantes nitrogenados tiene otras implicaciones desde el punto de vista de contaminación de acuíferos y demás, por procesos de lixiviación básicamente de algunos compuestos que se dan durante el desarrollo del ciclo del nitrógeno. Listo. Ya viendo el tema de materiales y métodos, queremos comentarles que partimos del hecho de que estamos ubicados en la zona media del Valle del Río Cauca, zona rural del municipio de Cerrito Valle, y el proceso de medición lo realizamos utilizando las mediciones directas en campo a través de cámaras estáticas manuales. En la imagen ustedes pueden ver un modelo o una representación de una cámara desensamblada, en la cual se caracteriza porque la mitad de esta base, de este primer componente que es la base, va a estar enterrada en el suelo, y a esta se le acopla o se le coloca encima la tapa. Esta tapa pues es un cilindro abierto en una de sus extremidades, de tal manera que se genere una cámara que permita acumular o generar una condición, un microclima diferente, afectado principalmente por las emisiones ahí en el momento. Y están acompañados de una banda, que la banda lo que busca es de cierta manera contribuir a que el acople sea un poco más estable, el acople entre la tapa y la base, y además que permite evitar la pérdida de estos gases que a nosotros nos interesan analizar. Ya, esto es para las mediciones directas en campo. La siguiente etapa es el proceso de análisis o la determinación de la concentración de estas muestras de gases, y eso se hace a escala de laboratorio a partir de técnicas de cromatografía de gases. En cuanto al diseño experimental, nosotros tuvimos un diseño factorial 2×4, en el cual el factor 1 corresponde a dos zonas contrastantes. ¿Cómo se determinó ese contraste o a partir de qué? De la caracterización de la conductividad eléctrica aparente en el suelo, en el cual nosotros establecíamos una zona 1 con menor conductividad en comparación con una zona 2. En la representación, la imagen que ustedes ven acá es una fotografía y encima hay una representación del proceso de interpolación de este proceso de zonificación. ¿Qué hicimos? Primero se hizo una caracterización del suelo a partir con un sensor de conductividad y con esta información lo que hicimos fue, utilizando sistemas de información geográfico, lo que hicimos fue interpolar esta información para generar una condición de superficie y posterior a eso hicimos un proceso de zonificación a partir de dos escenarios contrastantes y este fue el resultado. Una zona con baja conductividad y una zona con alta conductividad. ¿Por qué utilizamos la conductividad eléctrica aparente? Primero teníamos la disponibilidad del sensor que nos permitía abarcar grandes extensiones de terreno o más extensiones de terreno, tener suficiente información y que la conductividad eléctrica aparente, según la literatura, está muy ligado, tiene una correlación directa tanto con el contenido de humedad del suelo como con la proporción de texturas finas en el suelo y la condición de salinidad del suelo. Estos tres aspectos fueron factores determinantes porque nos permitían ver un escenario de contraste dentro de las dinámicas que se generaban en el suelo. Principalmente regulado por la humedad del mismo. El segundo factor que tenemos son cuatro sitios o 4 ubicaciones de las cámaras dentro del mismo cultivo, teniendo en cuenta o teniendo un factor es que sea la incidencia de las diferentes fuentes de nitrógeno que hay en el cultivo. Entonces, el tratamiento 1 fue un tratamiento denominado un tratamiento control, en el cual nosotros en el surco del cultivo instalábamos la cámara y en esa zona teníamos la influencia de 12 kilogramos por metro cuadrado de basura o residuos de cosechas anteriores. Cabe aclarar aquí un punto y es que nosotros la investigación la desarrollamos en un cultivo, un cultivo ya establecido, es decir, en una soca, ¿sí? Nosotros no empezamos con procesos de mecanización y demás, sino que acabó el proceso de cosecha y inicia de una vez el proceso productivo. Entonces, por eso nosotros contamos con incidencia de volúmenes de residuos de cosecha anterior denominados basura. El tratamiento 2 ya es una cámara instalada en el espacio entre dos surcos y en esta zona está bajo la influencia de 24 kilogramos de óxido nitroso. Estas dos, el tratamiento 1 y 2 es con fuentes netamente orgánicas de nitrógeno, es decir, la única fuente de nitrógeno en estos dos tratamientos fue el proceso de descomposición, el nitrógeno disponible a partir del proceso de descomposición de los residuos de cosecha o las dinámicas que se generan dentro del proceso de fijación por la disponibilidad de carbono en esa parte. El segundo tratamiento, el tercer tratamiento ya fue en el surco también, pero estuvo bajo la influencia de los 12 kilogramos de los residuos de cosecha más 30 gramos de nitrógeno por metro cuadrado. ¿Qué sucede? Que aquí nosotros ya tenemos la incidencia o el efecto de las dos fuentes de fertilizante, tanto la orgánica como una fuente orgánica como una fuente sintética. Y el cuarto tratamiento es un surco, o son surcos en los que solo tuvimos la aplicación de los 30 gramos de fertilizante nitrogenado, es decir, solo el efecto de la fertilización sintética. En la imagen, la representación, nosotros podemos ver entonces cómo quedaba el tratamiento 1, cómo quedaba instalado, el tratamiento 2, el tratamiento 3 y el posterior tratamiento 4. Listo. La recolección de los datos en campo, bueno, pues aquí vemos una cámara instalada durante el proceso de muestreo. El muestreo se hace en un lapso de tiempo de 1 hora, en el cual se divide en cuatro tiempos: tiempo 0, tiempo 20, tiempo 40 y tiempo 60, en términos de minutos. Y en cada uno de estos tiempos se toma una muestra de gas y cada muestra va a un recipiente individual o un vial, denominado un vial, que está en una condición de vacío, de tal manera que nosotros podemos tener una muestra de la condición de la atmósfera dentro de la cámara, una muestra del gas que hay dentro de la cámara en los diferentes tiempos. Y acompañado a eso, nosotros tomamos un registro de la temperatura, debido a que con los datos o con los datos de la concentración de los diferentes gases, nosotros aplicamos la fórmula de gases ideales, una modificación de la fórmula de gases ideales para determinar pasar de una concentración de partes por millón a miligramos por unidad de área. Entonces, en este desarrollo queríamos mencionar que nosotros en total instalamos 38 cámaras estáticas, de las cuales 22 cámaras estuvieron instaladas en la zona 1 y 16 cámaras en la zona 2. Hicimos 21 procesos de monitoreo, o sea, los monitoreos los repetimos o lo hicimos 21 veces durante todo el ciclo productivo, y en total recolectamos 2.868 muestras para el análisis. Aquí podemos ver un video de las condiciones en las que estaba el cultivo, las condiciones en las que estábamos en campo a los 4 meses de establecido. Ya, por ejemplo, en los últimos meses que estuvimos en campo, este panorama era mucho más adverso. Nosotros vemos que este video fue tomado antes de iniciar el proceso de muestreo, por eso todas las 2 cámaras que ustedes ven ahí están todavía destapados. Ahí estábamos iniciando. Estábamos haciendo un proceso de limpieza para abrir el camino para poder transitar en medio del cultivo. ¿Qué sucede? Que es que por el desarrollo del cultivo y su estructura foliar es un poco difícil una vez ya el cultivo de cierta manera se entrelaza o se denomina cuando el cultivo ya cierra, que hay una cobertura total en el suelo, ya es un poco más difícil la movilidad. Y bueno, ya en términos de resultados, nosotros veíamos que en términos de flujo de emisión, nosotros vimos que hubo un comportamiento diferente en términos de las magnitudes o de los picos de emisión, tanto en la zona 1 como en la zona 2. Nosotros vemos que los picos de emisión en la zona 2 eran mucho mayores. ¿Y qué sucede? Esta línea punteada roja representa la primera aplicación de fertilizante nitrogenado. El fertilizante nitrogenado que les mencionaba se hizo en 2 dosis, al comienzo del ciclo productivo y más o menos a los 60 días del desarrollo del cultivo. Y las líneas punteadas azules representan la aplicación de riego por canales en el cultivo. ¿Qué sucede? Según la literatura, la variación o el incremento en el flujo de emisión se da inmediatamente después, o se empieza a presentar inmediatamente después de la aplicación de fertilizante nitrogenado. Es decir que incluso se recomienda hacer un muestreo intensivo durante los 3 o 4 días posteriores a la aplicación del fertilizante nitrogenado para mirar cómo es ese pico de emisión. Sin embargo, nosotros vimos que el cultivo o que la emisión durante esos 3 días, 4 días no fue significativa, no hubo una varianza significativa. La explicación es que debido a las condiciones meteorológicas en ese periodo de tiempo, nosotros pudimos inferir que el suelo estaba en una condición de estrés hídrico. Y al estar en una condición de estrés hídrico, lo que hacía era que se limitaba la disponibilidad de agua para el proceso de hidrólisis de la urea. La fuente de aplicación o la fuente de fertilizante que utilizábamos en este ensayo fue urea. Entonces el suelo requiere agua para hacer un proceso de hidrólisis y no contaba con ella. ¿Qué sucedió? Cuando ya hubo la primera aplicación del riego, nosotros vemos como el efecto de humedecer el suelo y de generar una mayor disponibilidad de agua empieza a hacerse evidente. Ya el pico más alto se alcanzó en el segundo riego, ¿sí? Que hubo un lapso de tiempo de 5 días entre cada uno de estos riegos. Y ahí fue donde tuvimos los mayores picos de emisión, porque ahí fue donde reaccionó gran parte de toda esa urea que se había aplicado en momentos anteriores, en periodos anteriores. La segunda variación, vemos que después de ese pico, la emisión vuelve a como a estabilizarse un poco, ¿no? Y volvemos a ver una leve variación, un poco menos significativa, después de la segunda aplicación de fertilizante nitrogenado. ¿Qué sucede? Aquí ya hay muchos factores que intervienen. El primero de ellos, que es que acá ya la mayor parte del suelo está cubierto, es decir, hay una menor incidencia, una menor afectación por las variaciones de las condiciones ambientales, porque aquí ya la vegetación empieza a generar una condición de microclima que hace que las condiciones en el suelo sean un poco más constantes y por eso no se generan así como unos picos grandes de emisión. Lo otro es que acá ya también el desarrollo del cultivo ya son plantas con 60 días que ya están con una capacidad mayor en la asimilación o la absorción de este fertilizante que se aplica al cultivo. Y bueno, ya vemos que el flujo de emisión ya no fue tan marcado. Sin embargo, nosotros vemos que ya los tratamientos empiezan a ver que predomina, por ejemplo, o que el tratamiento con los picos más altos fue el tratamiento 3, que es el que estaba bajo la incidencia del fertilizante nitrogenado y la condición o el fertilizante orgánico. Si bien todavía acá el análisis se hace un poco difuso en la medida en que este fenómeno pues varía mucho y es un poco inestable, el siguiente paso es hacer el análisis de la emisión acumulada, es decir, coger y hacer el análisis acumulado de todas las emisiones durante todo el ciclo que se analizó. En ese sentido, nosotros, les recuerdo que hicimos el análisis o que hicimos la evaluación durante 210 días, es decir, que los datos que les voy a presentar corresponden a emisión acumulada en un periodo de 211 días. Hago esta aclaración porque el cultivo de la caña es un cultivo de ciclo anual, ¿sí? Que se cosecha generalmente después de los 10, que se cosecha entre los 10 y los 12 meses de establecido, dependiendo de los requerimientos y las condiciones que ustedes. Pero bueno. Entonces, nosotros vimos que la emisión promedio, la emisión acumulada promedio en la zona 1 fue de 145 miligramos de óxido nitroso por metro cuadrado. Aquí sale a la luz o se permite evidenciar un aspecto importante, y es que este es un fenómeno con altísimo grado de variabilidad, ¿sí? Entonces, nosotros vemos ya cómo estos márgenes o estos rangos se empiezan a incrementar secuencialmente. Bueno, para el tema de la emisión promedio en la zona 2, nosotros ya vimos que era de 466 miligramos de óxido nitroso por metro cuadrado, con un coeficiente o con un rango de 317 miligramos. Esto ya es lo que les mencionaba, ya es algo muy alto. Empieza a hacerse evidente. Pero es alto por las condiciones del fenómeno. Bueno, en ese sentido, entonces nosotros podemos determinar que la emisión de óxido nitroso en la zona 1 fue menor al de la zona 2 en una relación de 1:3. Ya para cuando empezamos a analizar tratamientos, a comparar los tratamientos en la zona 1 y en la zona 2, vemos que mientras la emisión en el tratamiento 1 de la zona 1, o sea, desde el control en la zona 1 fue de aproximadamente 14 miligramos, teniendo en cuenta que el coeficiente...
Muñoz, sí, parce, eso es un equipo que se va a utilizar
en el tratamiento 2, el
allá.
coeficiente de variación estuvo cercano al 30, entre el 30 y el 40%, y hubo una emisión de 155 miligramos. Ahí concluimos que la emisión en el tratamiento 1 en la zona 1 es menor, consecuentemente, al tratamiento 1 en la zona 2, con una relación de 1:11. Es decir, que acá ya empezamos a ver unas diferencias bastante significativas, ¿sí? Ya cuando vemos los datos en términos del tratamiento 2, en las diferentes zonas, vemos que para el tratamiento 2 para la zona 1 fue de 104 miligramos con un coeficiente mayor al 50%, y en la zona 2, el tratamiento 2 fue de 337 miligramos, un coeficiente también muy alto. Entonces, aquí vemos que tenemos un dominio o una superioridad en las emisiones en el tratamiento 2 de la zona 2 sobre el tratamiento 2 de la zona 1, con una relación de 1:3 también, igual que en el valor promedio. En tratamiento 3, vemos que en la zona 1 hubo una emisión de 165 miligramos y en la zona 2 de 648 miligramos. Ya esto nos da una relación de 1:4, donde el tratamiento 3 en la zona 2 tuvo mayor emisión que en la zona 1. Y por último, el tratamiento 4, nosotros lo que vemos es que en la zona 1 fue de 178 miligramos y en la zona 2 fue de 479 miligramos. Esto nos da una relación de 1 a 1.27, a 1 a 2.27, 1 a 2.7, es decir, una mayor emisión de óxido nitroso en el tratamiento 4 de la zona 2 en relación al tratamiento 4 de la zona 1. ¿Qué sucede? Pues esta relación es constante en todos los tratamientos y es consecuente con los valores promedio. Sin embargo, también lo que queríamos resaltar es que, bueno, variaciones en condiciones entre suelos húmedos y suelos secos, el suelo seco puede tener la capacidad de generar 3 veces mayor emisión que en un suelo húmedo. De ahí la relevancia de empezar a establecer estrategias de manejo diferenciado de acuerdo a las condiciones de humedad del suelo. Siempre y cuando pues esté pensando en el desarrollo de estrategias de mitigación, y eso es lo que se busca en el desarrollo de esta investigación. Muchas gracias por su atención. Agradecemos al programa OMICAS y a las diferentes instituciones que contribuyen en el desarrollo de esta.
Listo. Listo, Manuel. Muchas gracias por la presentación. Muy chévere tus datos. Creo que no tenemos tiempo. Te voy a hacer una pregunta, ¿sí? Que es algo que me intriga y es, digamos, esa diferenciación tan marcada entre la zona 1 y la zona 2 siendo, digamos, como el mismo espacio, ¿sí? Porque no se fueron, digamos, a sitios de cultivo distintos, zonas distintas, sino es el mismo espacio. Entonces me intriga mucho la diferencia entre esa conductividad eléctrica entre la zona 1 y la zona 2, que evidentemente influenció todos tus resultados. Entonces, ¿por qué se da esto? Manuel, tienes el micrófono cerrado. Por favor, que le abran.
Buenos días, qué pena. Bueno, Mauricio, el tema es que la emisión es un proceso altamente sensible a variaciones de temperatura y humedad en el suelo, ¿sí? También relacionado obviamente al contenido de nitrógeno en el mismo. Entonces, las condiciones que rigen los procesos de nitrificación, que es el proceso biogeoquímico donde se produce el óxido nitroso, es favorable en condiciones anaerobias, ¿sí? Porque la producción de óxido nitroso o la mayor producción de óxido nitroso se da mediante procesos de reducción, ¿sí?
Okay.
Entonces, esas variaciones en términos de conductividad eléctrica que las asociamos a humedad y a otras variables, es lo que nos genera una condición un poco más, mayor concentración de oxígeno en los espacios en el suelo, en el perfil del suelo, en relación a que la zona 2 tenía mayor condición de humedad, ¿sí? Entonces, es decir, todo el nitrógeno que llega en función de amonio inicialmente cuando uno aplica la urea, empieza ese proceso de oxidación hasta llegar a nitratos, ¿sí? Una vez esa oxidación se da, empieza el proceso de reducción. Entonces, todos esos nitratos, que es como esa condición de descomposición aerobia, ya quedan listos para empezar su reducción, ¿sí? Entonces eso es lo que genera ese factor diferenciado, y es que con el nitrógeno pasa algo, y es que es un proceso muy rápido. O sea, esto es decir, tú haces la aplicación de urea y en 2-3 días tú ya tienes una concentración altísima de nitritos, que ahí viene otro efecto, y es que se puede lixiviar, se puede perder en el suelo por lixiviación, pero que si tiene una condición favorable en términos para la reducción, de una vez va a empezar su proceso de reducción. La idea es que nosotros pudiéramos acelerar, una de las estrategias es que nosotros pudiéramos acelerar tanto el proceso de reducción para lograr que pase de óxido nitroso, o sea, pasa de óxido nítrico a óxido nitroso y después pasa a nitrógeno diatómico, que nosotros pudiéramos acelerar ese proceso, o que de cierta manera mejoráramos la capacidad de asimilación del nitrógeno durante el proceso, o que limitáramos como esa condición de humedad, ¿no? Entonces, por eso es es un proceso, y por eso es que es un poco más complejo tratar de estimar a través de modelos teóricos o modelos computacionales y demás, estos procesos de emisión, ¿sí? En ocasiones uno varía mucho.
Dale, listo, muchas gracias Manuel, pues esperemos por tus resultados cuando midan emisiones ya en todo el ciclo de cultivo, a ver qué obtienes ahí.
Sí, afortunadamente ya dentro del segundo ciclo de evaluación hemos podido articularnos o incluir variables asociadas a las dosis de fertilización, pero ya a mayor escala, ¿sí? Y ya empezamos a integrar también el tema de otras variedades para ver si el comportamiento si es constante o ese proceso de asimilación del nitrógeno juega un papel determinante en ese proceso de emisión.
Listo Manuel, muchas gracias. Entonces, muchos éxitos con el resto de investigación y gracias por tu tiempo y por tu charla.
Gracias.
Listo. So, let's move to our next speaker. So, our next speaker is Jorge Marin. He holds a degree in electrical and electronics engineering and a master of material sciences, and a PhD in electrical and computer engineering. In 2001, he joined the electronics and engineering program at the University del Quindío, and since 2002, he has been leading the research group on digital signal processing and processors at this university. So we welcome Jorge to this symposium, and we are looking forward to hearing you.
Good morning. In this presentation, I'm going to show the first result in a research that we are conducting at the University of Quindío. The primary goal in our research is the design of digital architectures that, using signal processing, are able to detect diseases on crops. Particularly for this paper, we are focused on rust, which is a very common disease on sugarcane crops. And to detect this disease, we are exploring here in this paper 3 different deep learning architectures for neural networks. The reason why we are interested on this kind of research is because the early detection of pests and diseases in a crop is very important to save money. Because if we are able to detect a disease in the early stage, we can act as soon as possible with a treatment to reduce the losses in production and also to improve the farmer's income. On the other hand, if we have a system that is able to detect a disease, we can use it to track the effectiveness of a given method to prevent a disease. So in this particular work, we are focused on rust disease, and rust looks like here, and in this picture, which has been taken from a leaf in a sugarcane crop. So, and it's estimated that in Colombia, between 4 to 10% of the financial losses are due to this disease, which means a huge amount of money. So our approach attempts to be used in a digital system like a drone. And basically, our idea is to include a signal processing on real time that, taking pictures from the crop, is able to apply some kind of learning machine methods to detect the presence of rust. So here in this paper, we want to use a cheaper solution that the very well-known solution. We know, for example, that multispectral cameras is a very useful technique to detect disease in a crop, but multispectral cameras are very expensive. So here in this particular paper, we want to find a cheaper solution. And our solution attempts to use a visible range image. That means that we use a regular camera on RGB space, and we want to use here to process these images deep learning neural networks. The reason why we are using these neural networks is because in deep learning neural networks, we can avoid the use of feature extraction. If you are familiar with feature extraction in in a system, you know that is a very important part in a system recognition, but the design of a very good feature extraction system is very difficult. So the deep learning neural networks provides a way in which you can avoid the usage of this stage just by using as input to the neural network, just the raw data. That means the pictures taken directly from the camera. So our paper here tries to show that, attest the hypothesis that it's possible to detect RAS in the visible range images using deep learning neural networks. So, and this is something that we want to check here because we haven't found any kind of prior studies in this particular problem. So basically, to do our research, we started by collecting a database to perform the training and validation of the neural network. And our database was collected using images available on different sources, available on internet, pictures taken from crabs in Colombia. And in total, we got at the end 820 images. The 50% of them are images from lips in the visible range, that includes rust, and the remaining 50% are healthy lips. To avoid overfitting, we use a procedure called augmentation. Basically, augmentation, we can use this kind of methods like horizontal and vertical reflection, sharpening, and contrast enhancement, and to get the final set composed by more than 9,000 images. These images are split on 3 data sets. The first data set includes the 80% of the images was used for training, and the remaining 20% of the images were used for validation and testing. Well, in this paper, we were checking 3 different models for convolutional neural networks. The first model is using an approach based on the design of a network trained by scratch. It means that we design to configure manually the input layer, the convolutional layer, the reduction layer, and classification layer. Particularly in this paper, we have to set up more than 2 million parameters, more than 2 million weights, and all weights were initialized randomly. On the other hand, we can use another approach that is called learning transfer. And learning transfer is a very well-known technique used in a convolutional neural network. Particularly here, we use 2 models that have been already proposed in the literature, inception V3 and inception ResNet V2. For example, in the case of inception V3, basically this network is a network that has been trained with a huge number of images and a huge number of classes. Basically, what we did here with learning transfer was to use this pre-trained network, and we replace the output layer just to detect 2 classes in our case, RAS and healthy lip. And we train this network with our own data set. We do that for inception V3 and inception ResNet V2. In addition of these architectures, we explore the use of different methods to avoid overfitting. It's very well known that convolutional networks are experience this kind of problem. Overfitting means that once you are training your network, sometimes the network attempts to memorize the training data set. That means that once you memorize the training data set, the network is not able to generalize. It means that if you show a different image that is not included in the data set, the network may be confused with. And that way, overfitting could be replaced by using different methods such as dropout, regularization, and the use of a different size for the batch. And we can also use early stopping and insertion of control points to avoid overfitting. The last one means that we monitor the validation and the training losses. And if we find a significant difference between the training loss and the validation loss, we can just decide to stop training and train again. Well, in addition to the training of these models, we also perform in this paper an analysis the robustness against adversarial attacks. And adversarial attacks means that we can include noise to the training dataset in such a way that this noise get corrupted the results for the neural networks. Even though that is a kind of artificial way to create an attack to the neural network, we can use the adversarial attack as a way to check out the robustness of the system under different environmental conditions. For example, in a real application, sometimes the pictures may be taken with a camera in a sunny day or sometimes in a cloudy day, and those kind of environments may introduce some kind of noise in the system. So we want to emulate this kind of noise presence, including adversarial attack. So in this way, including adversarial attack is a way to emulate this kind of noise. We can just use this technique to check out how efficient is the accuracy for our proposed method to detect rust in the presence of this kind of noise. So, and for that, we explore the fast gradient size method to build these adversarial images. So let's move down with our results. The first result is for the network trained by scratch. Remember that in this case, we need to set up different parameters, and here we are using 3 convolutional layers. We are also using a max pooling layer. For the neurons, at the end of the day, we use the leaky ReLU activation function. And for the output layer, we use the cross entropy loss function for classification layer. So the first step was to decide which optimizer use in our train. We tested 4 optimizers, which are shown here. And for the training data set, we are showing here the accuracy, that means the percent of the detection. And also we are checking here the training loss. We can see here that all the optimizers provide a very good result. In all cases of the optimizers are getting a percent accuracy higher than 90%. On the other hand, we can see here in the training loss that these two are MSPROP and ADAGRAD. They provide the best performance in terms of training loss. At the end, we decide to use ADAGRAD. And this method was used for the next results I'm going to show. So another strategy that we need to decide in this network from scratch is to explore a different activation function. We explored 3 alternatives, and at the end, we found that the ReLU and the leaky ReLU, they provide the best performance. However, at the end, we decide to use leaky ReLU because in leaky ReLU, for negative inputs, we can get some kind of activation of the neuron. That means with using this method, all neurons are already active. Instead of ReLU, in ReLU, some neurons may be active and others may be asleep. So that means that leaky ReLU ensures that all neurons are working in parallel. That is a desirable feature. So to avoid overfitting, we explore the use of regularization. Basically, there are 2 regularization norms, L1 and L2. We explore both, but L2 matches our problem statement. So particularly here, we can see that using regularization for the training and validation dataset, we can see here that on green, we have without regularization, or red with regularization. So we can see here that regularization ensures that the results for the training and validation dataset are more coherent. That means that the generalization is performing better using regularization than without using that. And this result is also coherent with the losses. Here we can see that the losses for the training and validation dataset are very similar. That means that the system is doing a very good job to avoid overfitting. So another strategy that we adopted to avoid overfitting was the use of dropout. Dropout means that during training, some neurons are frozen, so those neurons are not trained. So in particularly for these experiments shown here, we decide to use the 20%, 25% of the neurons are frozen during training randomly. And at the end, we found that if we use dropout, the losses from the training and validation datasets looks very similar. But if we don't use dropout, we can see here that the validation losses are increasing once the iteration increases. That means that here we are dealing with overfitting, but overfitting can be avoided by using dropout. Well, now let me show you the results with the learning transfer models. Particularly here, we choose these two models in section V3 and in section ResNet V2. What we did here was to replace the output layer for two classes, RAS and healthy lips. Here we can see that in these particular networks, we need to decide the number of hidden layers that are frozen during the training. And we performed some kind of experiments, and we figured out that if we frozen around like 67% of the layers on the insertion V3 network, we can get generalization. For the other numbers of freezing layers, we didn't get generalization. Similarly, for the ResNet V2, we found that if we freeze the 97% of the hidden layers, we get generalization. So if we compare the three models in terms of accuracy and losses for the training dataset and the validation dataset, we found that in the case of validation dataset, the accuracy for all the methods looks quite similar. In fact, the accuracy is around 90%, which is a very good number. Also, if we compare these results in terms of losses, we can see here that all networks are generalizing. That means that we are not dealing here with overfitting. On the other hand, if we compare the training loss and the validation loss, the network from scratch provides more coherent values. There are this line here on green from the training loss and validation loss are very similar, which is not the case for the other models. So that means that the generalization is performed better with the network from scratch. However, we need to check it out that if we perform different trainings, if we compare the final results, we found that the insertion V3 network provides a better performance, because every time that we train the network, we get a very good performance, around like 97% for the training dataset, and then 91% for the validation dataset. So, which is not the case for the other two models. So finally, we want to perform an adversarial attack. Remember that the adversarial attack means that we introduce some kind of noise to the original image in such a way that the images after noise addition looks quite similar to the original ones. For a human, it's basically the same, but for a learning machine, it's completely different. That means that this noise is added in a way that, for example, if this image corresponds to a rust, means that once we add the noise, the learning machine is identifying this one as a healthy leaf. So once we include this analysis and we want to include these noises to the training data set and we check it out the output from the neural network, we found that the network built from scratch provides the worst performance. In this case, we are getting initially without, before the attack, we have an accuracy of around 80% and it's decreased to 10%. On the other hand, this model based on insertion V3 provides the best performance because after the attack, the accuracy was reduced to 66%. So particularly the reason why insertion V3 is not seriously affected by adversarial attack is due to the fact that it includes a large number of trainable parameters, which is a result that has been already described in literature. Instead of the network training from scratch, it includes the less number of parameters. However, although the training, the network training from scratch provides the less number of weights, which means less computational effort, in terms of adversarial attacks, is showing us that it's not a good metric for that. Even though the results for the accuracy, all of them are showing very good results. In conclusion, we can see here that it's possible to use deep learning techniques to detect rust in visible in image on the visible range. And also we have found that all models provide an accuracy around 90%. We can also use overfitting to avoid overfitting, sorry. We can use altitude regularization, dropout, and early stops. And we can see here that by comparison between these three models, we have found that all models are showing very good performance in terms of accuracy, but in terms of adversarial attacks, the network from scratch is highly affected because it includes the lower number of parameters to be trained. So here it is my presentation. This is my contact information, and thank you.
Jorge, thank you very much for your presentation. So we have time for some questions. So I have some questions for you. So okay. How it's possible to make a distinction between these brown spots that are caused by the Ross disease and some other brown spots that could be associated with different factors, some other diseases or some environmental factors? Because this can be noise for your results.
Yeah, this is a very good question. So actually, our first motivation was trying to identify the rust presence in a crop. So basically, what we want is to this kind of processing will be included in a system which in real time is taking different pictures around the crop. So basically what we want to do is to take some pictures in such a way that we collect and we mark some particular parts in the crop that the learning machine is trying to tell us that there is a kind of disease in this particular part of the crop. But at the end, if we provide this information, which is geolocalized, we then provide some information that at the end the farmer, some people who is specialized in this kind of things, go directly to this part of the crop and they can verify that actually there is a presence of rust or not. Basically, this the idea is to use this kind of automatic system to try to identify where the person is there or not, in such a way that we can provide some information that at the end an expert is able to detect and to decide, okay, actually it's a rust or it's not rust. It's basically we with this kind of method we are not trying to avoid the use of a human to take the final decision. Basically, it's like a way to get an early information for the expert.
Okay. Okay, Jorge, thank you very much. And another question. Um, I'm not an expert on the field, but how do you decide what kind of noise are you going to add to the pictures? Because I can assume that there are different kind of noises that you can test in your system. So how do you decide what kind of noise are you going to add to your pictures?
Okay, so the adversarial task is something that has already studied on the literature, and it's not that the linear features of the learning machine. They provide a way that you can generate artificially a noise. So basically, this noise is created artificially based on the assumption that you want to corrupt an image. So there is an algorithm that basically you can do some kind of back propagation or regression to compute a kind of noise that provides the corruption for the network. So there are very well-known methods to do that. So it's not a randomly noise that we add to the image. No, that noise is particularly designed for the network to get corrupted. So basically what we're trying to do is to do a noise that for a human, the picture looks quite similar to the original image, but for a learning machine, the noise is adding in a way that the machine gets confused. So basically there are methods to create the noise artificially. It's something that has been already studied on the literature.
Okay, Jorge, it's much more clear for me. So thank you very much for your time, and thank you very much for your presentation. Good luck on your research.
Okay, thank you very much.
Okay, so let's move on to our next speaker, who is Alba Rocío Corrales. So she's a PhD in genetics resources of plants and associated microorganisms, a teacher and researcher at the Santiago de Cali University. She has experience in plant biotechnology and tolerance on abiotic stresses and in economically important crops. She is leader of the research group in industry and environmental microbiology at this university. So we give you a warm welcome to you, Alba, and we are looking forward to hearing you.
Buenos días, mi nombre es Alba Rocío Corrales. A continuación les voy a presentar el trabajo titulado Aproximación metagenómica para la identificación de comunidades endófitas de raíz de yuca, manejo de esculenta crans bajo condiciones de estrés abiótico. Este es un trabajo que se realizó en colaboración con el CIA, la Universidad Nacional y la Universidad Santiago de Cali. Durante los últimos años, uno de los principales problemas que ha afectado la producción de cultivos a nivel mundial es el estrés abiótico. Se estima que de las 5,2 billones de hectáreas que están destinadas a la agricultura, el 64% está afectado a causa del estrés por déficit hídrico. Este tipo de estrés causa una serie de efectos negativos sobre el rendimiento y la producción de los principales cultivos de importancia económica a nivel mundial. El estrés por déficit hídrico en planta provoca una serie de efectos a nivel fisiológico y metabólico, como es una reducción de la tasa fotosintética, un aumento en el cierre de estomas, una disminución de la transpiración, y también produce un efecto negativo sobre la diversidad de comunidades microbianas en torno a la raíz de la planta y en el suelo. Durante los últimos años se han estudiado cuáles son las comunidades microbianas que pueden tener un efecto positivo sobre el crecimiento y desarrollo de la planta. Dentro de estas comunidades microbianas se han estudiado en mayor detalle las bacterias promotoras de crecimiento vegetal, ya que ellas tienen unas características particulares que permiten contribuir al adecuado crecimiento de la planta, como producción de síntesis de sideróforos, fijación de nitrógeno, síntesis de auxinas, citoquininas, gibberelinas y solubilización de fosfato. La mayoría de bacterias que están dentro del grupo de las PGPRs pertenecen a los filos Proteobacterias, Chlorofex, Actinobacterias, Acidobacterias, Bacteroidetes, Plactenomyces y Firmicutes. Todos estos filum se conocen en la actualidad que tienen miembros de este grupo que se llama PGPR y actualmente se ha estudiado que ellas también juegan un papel importante en la respuesta a estrés abiótico en plantas y particularmente en el estrés por déficit hídrico. Durante los últimos años también se han abordado nuevas estrategias biotecnológicas para mejorar y para mitigar el impacto causado por el estrés abiótico y en particular por el déficit hídrico. Se han hecho estudios de transgénesis, genética reversa y actualmente se están haciendo muchos estudios a nivel metagenómico para conocer esa diversidad microbiana y cómo puede tener un efecto positivo frente al estrés por déficit hídrico. En este sentido, se han abordado estudios de metagenómica en plantas de interés agronómico como es arroz, tomate, patata, trigo, y se han podido identificar que algunos consorcios bacterianos pueden tener un papel importante en la tolerancia a estrés abiótico en plantas y particularmente en el estrés por déficit hídrico. Es así como nosotros quisimos estudiar la diversidad microbiana en un cultivo de importancia económica como es la yuca, puesto que la yuca es el cuarto cultivo de mayor importancia económica después del arroz, trigo, maíz, tiene altos contenidos nutricionales y es un cultivo que se genera en áreas tropicales y subtropicales del mundo. Adicionalmente es un cultivo que ya se conoce que tiene un grado de tolerancia a estrés abiótico, en particular déficit hídrico. Teniendo en cuenta que la población mundial está creciendo de una manera exponencial y en las próximas décadas vamos a tener mayor demanda de alimentos y la disponibilidad de agua para la agricultura es cada vez más reducida, pues nosotros quisimos estudiar la diversidad microbiana en este cultivo de la yuca. Es así que el objetivo general de nuestro trabajo fue identificar las comunidades endófitas de la raíz de yuca, Manihut esculenta crans, bajo condiciones de estrés por déficit hídrico a partir de un análisis metagenómico. Nosotros inicialmente utilizamos el cultivar MCOL 1734, que fue un cultivar proporcionado por el grupo de genética de yuca del CIAT, donde este cultivar ya había sido evaluado en campo y tenía un grado de tolerancia a estrés por déficit hídrico. Nosotros utilizamos 10 plantas del cultivar MCOL 1734 y realizamos los ensayos de déficit hídrico bajo condiciones de invernadero. Nosotros inicialmente tuvimos plantas de 4 semanas que fueron crecidas en condiciones control con un riego constante y posteriormente un grupo de estas plantas fue sometido a estrés por déficit hídrico entre un periodo de 20 y 30 días. Nosotros posterior al ensayo de estrés tomamos raíces laterales y adventicias, hicimos una esterilización de la raíz para poder solo identificar las bacterias endófitas y se hizo una extracción de ADN total. Se envió a un servicio de análisis metagenómico con la empresa Novogene solicitando la amplificación de las regiones B3 y B4 para amplificar el gen 16S ribosomal de bacterias. Una vez obtenidos nuestros resultados, nosotros hicimos un procesamiento de los datos crudos, en donde en primer lugar hicimos un análisis de la calidad de secuencias con el programa FastQC, posteriormente hicimos una eliminación de las quimeras y con el algoritmo Shem y seguido hicimos un análisis con la base de datos Silva. Nosotros pudimos obtener un grupo determinado de especies endófitas bacterianas y pudimos categorizarlas en agrupación por otros. También hicimos alineamientos múltiples con el algoritmo Mosul y análisis filogenéticos con el programa MEMCA. Posteriormente hicimos análisis estadísticos de alfa y beta diversidad con el programa KIM2. Como resultados, inicialmente pues se evaluó la calidad de las lecturas obtenidas a partir de el análisis de 5 muestras, 5 plantas que fueron utilizadas como control al inicio del ensayo y 5 plantas que fueron utilizadas para el tratamiento del estrés por déficit hídrico. Obtuvimos un aproximado de 354.422 lecturas. Adicionalmente, todas nuestras lecturas tuvieron un tamaño aproximado de 407 pares de bases y analizamos los índices FIRET superior a 80. Para Q20 tuvimos aproximadamente más del 96% y Q30 superior al 90%. En cuanto al porcentaje de guanina citosina, tuvimos un 55,64%. También analizamos las curvas de rarefacción de las 10 muestras obtenidas, puesto que el análisis que se había solicitado era de 50.000 lecturas. Nosotros observamos que todas nuestras muestras llegaron a una asíntota de 50.000 lecturas, lo cual eso nos garantizó para poder obtener 18 filums, 198 géneros y 80 especies. Adicionalmente, hicimos un análisis de abundancia relativa del filum de bacterias endófitas de yuca y pudimos observar que hubo 4 filum predominantes: proteobacterias, firmicutes, bacteroidetes y actinobacterias. Con respecto a plantas control que se utilizaron al inicio del ensayo, pudimos ver que al inicio hubo una ligera disminución del filum proteobacterias. Al comenzar el ensayo tuvimos 54.74% y al finalizar un 37.34%. Con respecto al filum firmicutes hubo un aumento en abundancia. Con respecto al final del ensayo pasamos de 40.39 a 57.09. Con respecto al filum bacteroidetes, hubo una ligera disminución de un 0.85 a un 0.32, y con respecto al filum actinobacterian hubo un ligero aumento de 4.02% a 5.24. Con respecto a plantas que fueron expuestas a estrés por déficit hídrico, al inicio y al final del tratamiento observamos que del filum proteobacterias hubo una ligera disminución, del filum firmicutes hubo un aumento del 4.36% al 7.86%, del filum bacteroidetes hubo un aumento del 0.65 al 3.46%, y del filum actinobacterian hubo del 2.31 al 2.50. Cabe destacar que estos filum son predominantes de bacterias endófitas y pues están muy asociados también a algunos grupos de bacterias promotoras de crecimiento vegetal. También hicimos un análisis de abundancia relativa del porcentaje de los principales géneros aislados de raíz de yuca. Los géneros que pudimos observar, por ejemplo, con respecto al filum actinobacteria, predominó el género Streptomyces, que en plantas expuestas a estrés por déficit hídrico se observó que tuvo un aumento de un 57%. Este género es muy característico de bacterias que pueden producir compuestos tipo indol que están asociados a la ruta del ácido indol acético. También observamos el filum bacteroidetes y se observaron otros géneros característicos como es el Chrysobacterium y el Spinobacter, que son géneros que están asociados a comunidades endófitas y se han observado en estudios metagenómicos realizados en especies de interés agronómico como arroz y como trigo. También dentro del filum firmicutes predominó el género Ruminicocose, que es un filum que es característico por tener miembros y especies fijadoras de nitrógeno y solubilizadores de fosfato. Y por último, el filum más abundante, proteobacterias, que tenían miembros del género Acinetobacter, Encifer, Pseudomonas sphingobium, que están asociados a fijación de nitrógeno, solubilización de fosfatos, producción de sideróforos, producción de compuestos tipo indol. Entonces, y muchas de estas especies están consideradas y están caracterizadas como bacterias promotoras de crecimiento vegetal. Adicionalmente, se hizo un análisis de composición de comunidades microbianas y se hizo una selección de 37 especies que tenían un porcentaje de identidad superior al 97%. De estas 37 especies se observó que 16 especies estuvieron en todo el ensayo, tanto al inicio y tanto al final, y en plantas control y en plantas expuestas a estrés por déficit hídrico. Cabe destacar que de estas predominan especies como Pseudomonas, que se conoce que son bacterias promotoras de crecimiento vegetal y pueden estar implicadas en la tolerancia a estrés abiótico. También en plantas control encontramos solo 2 especies que estuvieron al inicio del tratamiento, y en plantas que posteriormente fueron expuestas a estrés por déficit hídrico encontramos 3 al inicio del ensayo. También en plantas control al final del tratamiento encontramos una sola especie, y particularmente, interesantemente, en plantas que fueron expuestas a estrés por déficit hídrico por un periodo de 20 días, encontramos 3 especies características: Clostridium sp, Acinetobacter uofi y Acinetobacter sp. Estas bacterias están caracterizadas como PGPR, están asociadas a producción de compuestos tipo indol, y interesantemente también se han estudiado que estas especies tienen un grado de tolerancia al estrés por déficit hídrico, hídrico, lo cual es muy interesante. Pueden utilizarse más adelante como especies o bioindicadoras o especies que puedan utilizarse para mitigar los efectos causados por el estrés. Adicionalmente, hicimos un análisis filogenético con estas 37 especies y pudimos determinar que están agrupados en 4 grandes clados: proteobacterias, bacteroidetes, actinobacterias y firmicutes. Todas estas especies, la mayoría, están categorizadas como especies endófitas y especies que pueden ser PGPR, y algunas de ellas también se conoce que tienen un grado de tolerancia a estrés abiótico. Adicionalmente, pues también se hizo un análisis de componentes principales porque queríamos mirar la densidad de las poblaciones y la diversidad microbiana encontrada en el análisis. Nosotros observamos que las plantas que se utilizaron para el inicio del ensayo y plantas control estaban con una densidad completamente diferente a plantas que fueron expuestas a estrés por déficit hídrico, lo cual nos ratifica que estas plantas y esta densidad de especies son características de en estos ambientes. En este sentido, nosotros quisimos plantear un set de especies que pueden utilizarse en programas de mejora y se pueden utilizar como especies indicadoras, o también a futuro se pueden utilizar como especies inoculantes en cultivos que estén expuestos a estrés abiótico. Tenemos especies como Acinetobacter y Pseudomonas alcaligenses, que son del filum Proteobacterias, especies como Chrysobacterium indulgens, perteneciente al filum Bacteroidetes, especies como Nocardia veterana del filum Actinobacteria y especies como Clostridium sp del filum Firmicutes, que pueden utilizarse en programas de mejora para mitigar los efectos causados por el estrés abiótico. Adicionalmente, también se pueden utilizar como inoculantes en cultivos no solo de importancia económica como la yuca, sino de otros cultivos que puedan requerir biofertilizantes para mitigar los efectos causados por el estrés. Entonces, en este sentido, esto es una excelente estrategia biotecnológica. Así como conclusiones, nosotros pudimos determinar que 4 filum tienen una mayor prevalencia bajo condiciones de estrés por déficit hídrico como proteobacterias, firmicutes, bacteroidetes y actinobacterias, y que algunos de ellos pertenecen al grupo de PGPR, y son bacterias endófitas, que los géneros Bacillus, Bacteroidetes, Streptomyces y Pseudomonas son categorizados como PGPR y presentan una gran abundancia tras el estrés abiótico, y que el análisis metagenómico mostró especies como Clostridium, Acinetobacter y Acinetobacter sp como potenciales bacterias promotoras de crecimiento vegetal que pueden contribuir al estrés por déficit hídrico. Como agradecimientos, pues a Alexandra Fernández y a Valentina Herrera, que son microbiólogas de la Universidad de Santiago de Cali, quienes fueron las que hicieron los ensayos bajo condiciones de invernadero, a la bioinformática de Ana Carolina López, que nos colaboró con la parte del análisis, al grupo de investigación en genética de yuca, que nos proporcionó el material vegetal y las instalaciones para realizar los ensayos, y a la Universidad de Santiago de Cali por financiar este proyecto. Muchas gracias.
Bueno, no, agradecer al doctor Alba por la presentación. Muy buen trabajo, muy completo. Entonces, pues tenemos aquí un par de preguntas de la audiencia. Pregunta Nicolás, ¿qué tan sensibles son estas especies a los cambios en pH que pueden causar algunos químicos aplicados en la agricultura, por ejemplo? Creo que eso pues pensado en una opción de si finalmente podemos agregar a los cultivos estas bacterias como forma de mitigación al estrés hídrico. Bueno, ¿cómo sería la interacción con fertilizantes, pesticidas? ¿Tendría alguna influencia sobre el efecto benéfico de estas bacterias?
Bueno, en primer lugar, buenos días. ¿Me escuchan?
Sí.
Bueno, buenos días. Entonces, bueno, para la pregunta de Nicolás, en cuanto a estas bacterias, el set de bacterias que mostró al final, que fueron identificadas, son bastante tolerantes también a otros agentes químicos. Hemos hecho algunos ensayos pilotos con suelos con un grado de intervención y han sido tolerantes, o sea, como para ser candidatas para programas de mejora o para utilizarlas como biofertilizantes, sí son tolerantes. Y pues la estrategia de haberlas utilizado frente a estrés por déficit hídrico es bastante interesante porque estas plantas, no solo yo en el trabajo lo hicimos a 20 y 30 días, pero normalmente pueden tolerar hasta 40 días de sequía. Entonces, soportan una carga de estrés suficientemente alta y en cuanto a la parte química también soportan. Como por ejemplo, estamos intentando hacer ensayos con glifosato, a ver si también tienen un grado de tolerancia a este agente.
Perfecto. Tenemos otro par de preguntas y es que si consideras que los grupos taxonómicos identificados mediante el método de agrupación por OTUS podrían variar significativamente si hubieras empleado algún otro algoritmo o método de agrupamiento, por ejemplo,
Sí.
DADA2.
Sí, nosotros lo hicimos por varios, de hecho lo hicimos por DADA y tampoco hubo muchas diferencias. Ahora estamos analizando, este trabajo que mostré solo era de bacterias endófitas. En estos momentos estamos procesando datos de bacterias rizosféricas y lo hemos comparado también con diferentes bases de datos, con diferentes análisis estadísticos y da muy similar a lo que acaban de observar.
Listo. ¿Qué métodos empleaste para hacer el análisis de abundancia diferencial? Y si estos métodos tienen algún soporte estadístico.
Si nosotros manejamos y lo hicimos generalmente hicimos de análisis diferencial, hicimos por el índice de Shannon, el índice de Shaw, bueno, más que todos los índices que se manejan para mirar diversidad y abundancia, hicimos por varios índices y generalmente nos salió, en cuanto a endófitas, no nos salió muchas diferencias significativas, o sea que las bacterias endófitas que encontramos fueron características y estas comunidades fueron características de estas plantas. Entonces no hubo muchas diferencias significativas frente a otros índices. ¿Y cuál era la otra pregunta?
Gracias.
¿Puedes repetir la otra pregunta?
Y finalmente, sí, dentro de tus perspectivas, ¿has considerado hacer análisis de genoma completo de aquellas comunidades de bacterias que resultaron ser definitivamente fundamentales para la respuesta al estrés?
Sí, nosotros tenemos en estos momentos, hicimos también, obviamente estos análisis de metagenómica, buscamos identificar esa diversidad no cultivable. También tenemos un set de aislados cultivables, tenemos aproximadamente 120 aislados, esos aislados están caracterizados algunos, otros aislados tenemos el set que mostré al final, que son de bacterias PGPR. Esas tenemos 19 aislados, sí, los vamos a secuenciar con tecnología Oxford Nanopore, con Minion, para mirar genes que puedan ser característicos, por ejemplo, solubilizadores de fosfato, fijadores de nitrógeno, que puedan estar implicados y que podamos validar estos resultados que les mostré y validar que realmente tengan genes máster o genes Diana que puedan estar implicados en la tolerancia al estrés por déficit hídrico o a estreses abióticos en general.
Claro, porque, o sea, que finalmente, digamos que la idea de todo esto es poder dar con los mecanismos, ¿no?
Ajá, sí,
Mirar
identificar genes.
molecularmente qué es lo que hacen estas bacterias con los cultivos para que bajo déficit hídrico, pues estas plantas puedan tolerar estas condiciones.
Sí, claro. Por ejemplo, lo dije en la charla, pero digamos algunas ya sabemos y están caracterizadas por bibliografía, que son solubilizadoras de compuestos indoles y estos están en rutas intermediarias de respuesta fisiológica al estrés y de hormonas. Entonces, lo que queremos es identificar esos genes, pues mirar algo de funcionalidad y pues ya a futuro ver algo de bioprospección, ¿no? Se pueden utilizar como biofertilizantes a futuro y se pueden emplear como bioprospección. Pues esa, digamos, sería como ya el producto final y realmente eso contribuiría mucho a la tolerancia a estrés abiótico en cultivos en general.
Ok. ¿Piensas hacer caracterización de otros cultivos o te vas a enfocar específicamente en yuca?
fue algo interesante porque, bueno, realmente utilicé yuca porque tenemos la disponibilidad del material vegetal y por la colaboración que estamos haciendo con el grupo de genética de yuca y porque estos cultivares habían estado evaluados hasta el cansancio en un ensayo en La Guajira, no lo comenté, pero estas plantas ya han sido, y ellas mismas seleccionan los microorganismos en campo, ¿no? Esto yo lo hice primero en invernadero por razones a fines prácticos, pero pues es interesante porque ya la yuca selecciona ese set de microorganismos y dice, bueno, yo trabajo con estos para mirar y tener un grado de tolerancia. Sería interesante verlo en arroz. He visto trabajos en metagenómica en arroz y se comparan mucho esa diversidad y esos géneros que yo les mostré también se han evidenciado en arroz y en trigo. Entonces se podría hacer un ensayo en arroz. Sí, me parece súper viable y pues también a nivel de agua, si estamos viendo algunas variedades que son más características, por ejemplo, con agua se podría observar y podría ser, o en lodos también se podría observar y sería muy interesante, porque ahí sí, dependiendo del área, asimismo se puede mirar diversidad microbiana y cómo puede estar teniendo un impacto sobre el crecimiento de la planta. Si el área tiene problemas de condiciones ambientales, ¿sí? Hablo temperaturas altas, bajas, salinidad, otros tipos de estrés abiótico.
No, Alba, muy buen trabajo, excelente trabajo. ¿Para cuándo sale la publicación?
Estamos en ello con pues, los colaboradores. Realmente cabe destacar que esto fue un trabajo de tesis de pregrado de 2 estudiantes de microbiología de la Universidad Santiago de Cali, y estamos trabajando con la Diana López, la doctora Diana López, que también es bioinformática, entonces esperamos que salga prontico.
No, pues espero con ansias de ver el trabajo publicado. Me llama mucho la atención que sea de estudiantes de pregrado, porque es un trabajo muy completo. Felicitaciones, de verdad, Alba.
Bueno, muchas gracias, Mauricio, y a ustedes por su atención.
Listo, muchas gracias,
Bueno.
Alba. Muchas gracias por participar. Okay, so let's move to our next panelist. So is Daniel Felipe Casas, who is a biologist, a member of the Applied Science Research Group of the Development of the Ecoregion at the University of Quindío. And now his work is focused on the application of basic science for the development of technologies in the Colombian agricultural sector. So welcome, Daniel, and we look forward to hearing you.
Buen día para todos. El siguiente trabajo se titula Efecto del suministro de nanopartículas de dióxido de titanio incorporadas con planta en el cultivo de espinaca. Fue liderado por el profesor Fernando Gordillo Delgado, líder del Grupo de Investigación en Ciencia Aplicada para el Desarrollo de la Ecorregión, y presentado por quien les habla, Daniel Felipe Casas Castañeda. Pertenecemos al grupo a la Universidad del Quindío. Tenemos pues que la espinaca ha sido ampliamente cultivada a nivel mundial. Sin embargo, para Colombia la espinaca se cultiva en las cordilleras, específicamente donde hay condiciones agroecológicas necesarias para su cultivo, como son los departamentos de Antioquia, Cundinamarca y norte de Santander, y en menor medida lo produce Boyacá. Existen varios desarrollos de la nanotecnología en aplicaciones específicas para la agricultura. Entre ellas tenemos las nanopartículas, que las utilizamos en este estudio, nanosensores y nanocápsulas. Otras aplicaciones que ha tenido la fitonanotecnología ha sido la reducción en la aplicación de fertilizantes, tanto de origen sintético como de pesticidas. También se ha utilizado la detección de patógenos por medio de los nanosensores. Se ha mejorado el incremento de la producción y optimización de nutrientes, ya que por medio de nanopartículas e incluso de nanocápsulas se ha permitido la liberación lenta y lo necesario por la planta para hacer rendir los nutrientes tanto en el suelo como los proporcionados. Y también se ha utilizado para el tratamiento de enfermedades, e incluso con otros materiales para la síntesis de las nanopartículas. Entonces, esto obliga a que se vea como una alternativa necesaria para la agricultura moderna y tradicional, y mitigando los impactos medioambientales que ha conllevado todo esto. Para esto, entonces nos planteamos sintetizar las nanopartículas. Empezamos con la técnica de Sol-Gel. Consiste en, primero, tener un líquido en donde vamos a tener un precursor de titanio. Posteriormente vamos a tener un gel que se obtiene luego de que el propanol se evapora. Una vez evaporado el propanol, pues vamos a tener un sólido. Este sólido se sintetiza a una temperatura y tiempo determinado, ya que van a ser variables indispensables para la caracterización de las nanopartículas. Una vez tenemos las muestras resultantes, se caracterizaron por DRX, SEM y EDX. Como resultados tenemos entonces que la composición elemental que tiene la muestra es en mayor medida oxígeno. Esto se debe principalmente a la forma en que fue medida la muestra. Tenemos titanio en igual cantidades, en lo que se buscaba, no buscábamos variar el dióxido de titanio, pero sí tenemos entonces que la plata, pues la buscábamos que fuera proporcional a lo que habíamos agregado, que era 0.25, 0.50 y 0.75. ¿Listo? Al lado derecho tenemos un difractograma característico de picos de dióxido de titanio en fase anatasa. Es importante porque vemos que la plata adicionada no varió la estructura del dióxido de titanio en este caso, que podría cambiar fácilmente a rutilo o bruquita. Las nanopartículas tuvieron un diámetro aproximado entre 9 nanómetros, tienen forma esférica y estuvieron aglomeradas con una superficie porosa. Es importante lo de la temperatura y el tiempo de exposición, ya que se ha documentado muy bien que las nanopartículas cambian en forma, tamaño, dependiendo de la temperatura a las que son sometidas a la hora de sintetizarlas. Aquí podemos ver que la estructura del dióxido de titanio cambió y eso influye directamente sobre el tamaño. Para los test de toxicidad de las nanopartículas sobre las semillas de espinaca, lo que hicimos fue obtener semillas certificadas por una casa comercial. Estas fueron lavadas para liberarlas de pesticidas y fungicidas que se le aplican para su almacenamiento. Una vez lavadas, se procedió a inocularlas con las nanopartículas a una concentración de 0.25%. Después de esto, se pasaron unos periodos de luz-oscuridad que consistían en tener 2 horas de luz, 2 horas de oscuridad, y así durante el resto del día por 3 días. Esto con el fin pues de que los rayos UV activaran el dióxido de titanio y permitieran que rompiendo la membrana de la testa de la semilla puedan introducir más agua y aumentar su germinación, como se evidenció en este caso. En la tabla 2 podemos ver los análisis correspondientes al porcentaje de germinación en el cual la casa comercial nos garantiza un 70% de germinación, fue lo que se evidenció, y se aumentó en hasta un 13%, el cual fue el tratamiento de TiO2 con plata adicional 0.75%. Vemos que los otros tratamientos también tuvieron un aumento significativo. El tiempo medio de germinación fue menor en días comparado con el control, y la tasa de germinación en el cual nos indica las semillas germinadas por día, pues fue mayor también con respecto al control, lo que evidencia un claro efecto de las nanopartículas sobre la germinación de las semillas. En la imagen de la derecha podemos ver las semillas con raíces y hojas cotiledonares totalmente sanas, características de su germinación. Para las mediciones morfoanatómicas, entonces, nuevamente tomamos las semillas, las sometimos a las nanopartículas en la misma concentración, se sometieron al periodo de luz-oscuridad, y estas semillas, después de inoculadas, se procedieron a sembrar en un sustrato inerte. El sustrato inerte tenía en mayor medida roca y algo de materia orgánica para simular los nutrientes que necesita la planta. Cabe resaltar que también se hicieron riegos y aplicaciones de fertilizantes, tanto edáficos como foliares. Para las variables morfoanatómicas, entonces tuvimos en cuenta altura, número de hojas emitidas y largo y ancho de la hoja para estimar el área foliar. Por último, se aplicaban también de forma de riego las nanopartículas en la misma concentración. Esto fue lo que tuvimos. En la gráfica A podemos observar la altura promedio de las plantas. Esta variable fue significativa, ya que comparado con el control, pues las plantas presentaron un que el número de hojas emitidas no fue significativo. Esto es bueno porque significa que no estamos alterando la morfología de la planta como tal, la disposición en la que crecen las hojas, que en este caso es en roseta. Tanto el largo y ancho promedio de la hoja no fue significativo, sin embargo fue positivo porque vemos que es en concordante con la altura de la planta, ya que si la planta es más alta, pues también se puede ver reflejado en el área foliar. En la imagen de la izquierda podemos ver entonces las plantas bajo cada uno de los tratamientos. Podemos ver que las plantas bajo los tratamientos fueron o presentaron mayor altura. Esto se debe principalmente a que las nanopartículas ayudan al proceso de absorción de nitrógeno y con anterioridad ayudan también al proceso de convertir el nitrógeno inorgánico a orgánico, lo que lo hace más asimilable para las plantas, y esto se va a ver reflejado también en el área foliar, en sus primeras etapas de desarrollo. La que mayor presentó altura fue el tratamiento de dióxido de titanio con plata adicionada al 0.75%, que presentó un aumento del 53% con respecto al control. Para la técnica fotoacústica tenemos que se compone de un computador, un loquín que nos amplifica la señal, un monocromador que nos va a dar una señal roja modulada y otro monocromador que nos va a dar la luz blanca. Aquí en la ampliación de la celda fotoacústica podemos observar que la hoja va a generar un vacío al ser colocada en la celda fotoacústica. Por el haz de la hoja vamos a incidir una luz roja modulada a una determinada frecuencia, y por el en vez de la hoja vamos a incidir una luz blanca a los 30 segundos de iniciar la medición. Esto va a producir un proceso en el cual la planta va a consumir dióxido de carbono y va a liberar oxígeno. Esta liberación de oxígeno se va a ver acompañada de una reacción fototérmica y va a producir una variación de presión. Esta variación de presión va a ser captada por un micrófono y amplificado directamente por el amplificador y visto en el computador. De esta manera se puede observar la señal de fotoacústica. En los primeros 30 segundos, como se muestra en el cursor, van a mostrar las señales que está captando de la planta. Posteriormente se enciende la luz blanca. Aquí vemos la caída que presenta la reo y vemos que hay un proceso de saturación. Después de 30 segundos, a los 60 segundos, volvemos y apagamos y vuelve y sube la razón de evolución de oxígeno y se va a mantener constante. De esta forma vamos a hallar la razón de evolución de oxígeno que está ocurriendo durante los primeros 90 segundos. Esto fue lo que tuvimos. La reo durante los primeros 35 días fue similar entre los tratamientos, pero diferente comparados con el control. Esto se debe a que hay un efecto significativo de las nanopartículas sobre las plantas. Luego del día 35 podemos ver que la reo en algunos tratamientos cae. Esto se puede deber a condiciones climáticas, tal vez el estado de desarrollo de la planta o por la cantidad de plata adicionada que tenía. que en este caso el único que se mantuvo constante fue el dióxido de titanio con plata adicionada al 0.25%. En la gráfica A podemos ver una gráfica típica de la señal de fotoacústica. Corresponde al día 49, en donde los tratamientos todos están similares. De esta forma, pues podemos estimar el arreo y monitorearla en el tiempo. Se han realizado aproximaciones de pruebas en campo. Esto se hizo en un municipio cordillerano, específicamente en Pijao, Quindío, ya que cumplía con las condiciones climáticas necesarias para el cultivo de la espinaca. Se sembraron las semillas. Luego de 10 días teníamos hojas cotiledonares. Estas son las plantas después de 20 días de germinadas. Vemos que los tratamientos o las plántulas bajo cada uno de las nanopartículas con la plata adicionada, pues podemos ver que presentó mayor área foliar y una mayor altura comparado con el control. En cuanto a las conclusiones, tenemos que el presente estudio reveló que las nanopartículas de dióxido de titanio dopadas con plata, usadas en este trabajo, pues tienen un efecto positivo en la germinación, el tiempo medio de germinación y la tasa de germinación de las plantas de espinaca, lo que demuestra una interacción directa entre el compuesto químico y el modelo biológico, que en este caso fue la espinaca. Por otro lado, se evidenció un aumento significativo hasta de un 53% en la altura de las plantas, así como también en el área de hoja foliar, en comparación con el grupo control. Esto indica que las nanopartículas inoculadas en las semillas tienen una consecuencia en el incremento y desarrollo de las plántulas de espinaca. Por medio de la técnica fotoacústica también se estimula el arreo de las plantas de espinaca bajo el efecto de la inoculación de las semillas con las nanopartículas. Durante los primeros 30 días se observó una tendencia al aumento en los valores del arreo. Sin embargo, únicamente por el tratamiento de las nanopartículas de dióxido de titanio con incorporaciones de plata al 0.25% se mantuvo este comportamiento, de manera paralela al del grupo control, que presentó durante el monitoreo los valores más bajos del arreo. Esto podría estar relacionado con un proceso de estrés causado por otros tratamientos con mayor contenido de plata. Agradecemos pues a OMICAS por los recursos necesarios para la realización de este trabajo y a la Universidad del Quindío por la financiación a través de los proyectos del 982 y 916. Muchas gracias.
Listo, Daniel. Muchas gracias por tu presentación.
Gracias, Mauricio.
Entonces, listo. Entonces, mientras esperamos algunas preguntas de la audiencia, yo tengo aquí un par de preguntas. Listo. Entonces, utilizaste como modelo biológico espinaca. Listo, específicamente por qué seleccionaron espinaca para esos experimentos.
Espinaca, bueno, aunque espinaca no se comportó muy bien por el modelo biológico utilizado, decidimos utilizar espinaca porque es una planta que está cultivada en Colombia y pues decidimos trabajar con ella porque realmente ya se cultiva y es necesario pues trabajar con plantas que sean de interés comercial. Podríamos divinamente haber trabajado con Arabidopsis thaliana, que es un modelo ampliamente utilizado a nivel mundial y que está muy bien caracterizado, pero pues como no es un cultivo como tal, entonces decidimos trabajar con espinaca.
Ok, si necesitas trabajar con Arabidopsis, me contactas, que yo te puedo prestar algunas para hacer experimentos.
Sí, sería genial porque Arabidopsis, pues como ya lo dije, pues está muy bien caracterizada a todos los niveles y pues ya tener una teoría de esta planta pues sería genial y hacer los análisis comparativos con cultivos como arroz, caña y en este caso espinaca.
Listo, ok. Daniel, digamos los efectos que viste sobre el crecimiento de las plantas, que tengan mayor tamaño, que tengan mayor área foliar, lo asociaste con nitrógeno, ¿no? Con mayor absorción de nitrógeno por parte de las plantas. Entonces, mi pregunta es si finalmente realizaste algún experimento para validar eso. Que en realidad las plantas que estuvieran absorbiendo las nanopartículas y que tuvieran un mayor tamaño, tuvieran diferencias en cuanto a la absorción de nitrógeno. O cómo asumes tú que, digamos, ese efecto directo en crecimiento es influenciado por el nitrógeno.
Bueno, eso es algo que leí en literatura, ¿sí? O sea, cómo las nanopartículas facilitan a que las plantas, por medio de las raíces y una microbiota que hay en el suelo, pues ayuden a transformar este nitrógeno inorgánico a orgánico y que posteriormente pues las plantas lo van a absorber. Es importante este nitrógeno porque en las primeras etapas de desarrollo de las plantas, pues ellas van a utilizar más nitrógeno para formar toda su parte aérea, y en este caso las hojas, que se vio evidenciado pues en el área foliar. Pero realmente no tuvimos la capacidad pues de mirar qué cantidad de nitrógeno pueden absorber las plantas.
Sí, pues digamos, esa sería algo interesante por hacer, porque bueno, lo tienes como hipótesis, pero pues deberías comprobarlo, porque igual las nanopartículas que están siendo absorbidas, pues estás en un sistema biológico y son múltiples las cosas que puedes estar afectando en ese sistema biológico para causar un efecto fenotípico. ¿Listo? Entonces, sea cual sea la razón por la cual estas nanopartículas están directamente afectando el crecimiento, toca comprobarlo. Puede que sea nitrógeno, no te estoy diciendo que no, pero sería necesario, digamos, establecer algunos experimentos que permitan evaluar cómo están utilizando el nitrógeno las plantas, control versus las plantas que utilizaste con nanopartículas.
Sí, claro que sí. Hay algo que hay que hacerlo, porque realmente sí es indispensable aclarar esa forma en que las nanopartículas ayudan a las plantas a absorber el nitrógeno. Es indispensable.
Sí, y pues digamos en ese sentido utilizar una planta modelo, digamos como Arabidopsis o incluso arroz, pues podría ser ventajoso porque ya hay muchas técnicas ya fijas para cuantificar, digamos, el efecto de ciertos nutrientes sobre las plantas. Entonces, digamos que sería más fácil evaluarlas que sobre espinaca, aunque pues también se podría trasladar experimentalmente cómo se hacen estas mediciones como con espinaca. Que en realidad, pues no es algo, tampoco es algo como tan complejo de hacer. ¿Listo?
Sí, claro que sí. En el grupo, pues actualmente estamos trabajando con banano, los dos cultivos de interés comercial y para OMICAS también, que es el arroz y la caña. Entonces estamos extrapolando este efecto de las nanopartículas a estos cultivos. Son trabajos futuros que van a realizar.
Ok, Daniel. Y mi pregunta final es, ¿qué quieren hacer con estas nanopartículas? O sea, ¿es simplemente utilizarlas así como están siendo sintetizadas, pues para mirar el efecto en plantas o, digamos, muchas ventajas que tienen estas nanopartículas es que pueden ser funcionalizadas y pueden ser funcionalizadas con distintos elementos para que vayan a blancos directos en algunas ubicaciones subcelulares de la planta para tener algún efecto? Entonces, a futuro, ¿qué piensan hacer con las nanopartículas? ¿Han pensado en la funcionalización con algún elemento específico, con algún químico específico? ¿Qué quieren evaluar en un futuro?
Pues inicialmente queremos medir qué efectos tienen estos sobre las plantas, anatómicamente, fisiológicamente, pero también qué efectos tiene sobre patógenos o plagas que pueden estar afectando las plantas. Podríamos estar haciendo unos agroquímicos que no sean tan invasivos para la planta y para el medio ambiente, como lo mencionaba en la presentación, ya que estas nanopartículas pues, se pueden focalizar a nivel de la planta, se pueden suministrar una vez en el ciclo de la planta, podría ser el proceso de la germinación, o una sola vez que se rieguen, y entonces no se desgastaría más material. Se podrían hacer algunos productos a base de nanopartículas. Ya se han desarrollado e incluso se han identificado algunos nanocompuestos orgánicos a base de plantas y de bacterias que están siendo también utilizados a nivel de nanoescala para la fertilización en cultivos.
Claro, claro. Todas esas son potencialidades de las nanopartículas, entonces pues que valdría la pena evaluar. Porque recuerda que, digamos, el esfuerzo que estamos haciendo en OMICAS es, digamos, para generar nuevas estrategias tecnológicas, y ahí incluye nanotecnología, pues, digamos, para garantizar, digamos, como lo mencionaste, cómo se puede mitigar los efectos secundarios que puede tener una fertilización. Entonces, obviamente, funcionalizando estas nanopartículas con fertilizantes que sean menos agresivos o que puedan entrar directamente a la planta y que sean disueltos en el suelo, pues es algo que nos interesa. Entonces, pues muchas gracias por este esfuerzo.
Gracias.
Muchas gracias por este esfuerzo. Okay, so let's move to our next presentation. So the next presentation will be given by Amin Talesaida, who received a bachelor and master degree in mechanical engineering from the Amicavir University of Technology in Tehran in 2011 and in 2013, respectively. He is currently pursuing a PhD degree from the Sharif University of Technology in Tehran, and now he's visiting He is a PhD student visitor at the CST group and at Hoven University of Technology. His current research interests include optimal trajectory design, robotics, model-based design, and agricultural robotics. So welcome, Amin, to this symposium, and we're looking forward to hearing you.
Hello, everybody. This is Amin Taleizadeh, PhD student of Mechanical Engineering at Sharif University of Technology. In this paper, we want to discuss advantages and disadvantages of spraying drones. Nowadays, with continuously growing population, food production seems vital, and the need for food production and maintaining food security are more and more becoming issues. Traditional farm management cannot effectively respond to the nutritional needs of people. Moreover, various pests and plant diseases jeopardize sufficient plant products. By the help of agricultural modern technologies, new solutions can be offered to face these issues. In recent years, agricultural robotics has emerged to reduce hard labor and to improve efficiency using automation and mechanization. One of the most important aspects of robotics are unmanned aerial vehicle or UAVs, especially multi-rotors that have become very popular these days. UAVs can be used in many applications such as mapping, agriculture, delivery, cinematography, inspection, and many others. In these years, agricultural drones have helped to increase the productivity agricultural industry due to their advantages. Agricultural drones can be used for remote sensing, crop spraying, and field mapping. Agricultural spraying drones have become popular in recent years. These drones can spray 1 hectare in approximately 10 minutes, depending on its model, with only 10 liters. Using these drones can speed up the field spraying procedure and decrease water and pests usage. Spraying drones have many types in the market, which can be classified in liquid tank volume. Most types of spraying drones have a 10 liters liquid tank. However, some companies recently have launched new spraying drones with 16 liters, 20 liters, and 30 liters liquid tanks. In this picture, you can see a 16-liter spraying drone. Some agricultural spraying drones have collision avoidance system equipped with a DBF or digital beam forming radar. Some spraying drones have a first-person view or FPV cameras, and some of them can spray orchards using a 3D map which is generated with a mapping drone. In this picture, you can see that with a Phantom 4 RTK, you can generate a 3D map and put the 3D map file in the spraying drone, and the spraying drone use that 3D map and spray an orchard or a field with a high varying terrain. Recently, a new kind of these drones has been launched with which can spray the field smart using an NDVI map. Here you can see that an NDVI map. Some drones use these maps and spray smart, which is this map is generated with multispectral drones, and the spraying drone only spray on the fields which needs, not on the fields that they don't need any pests. Most of crop fields have some trees, power tower, or scarecrow, which the spraying drone's user can over these obstacles using two methods. First of all, the user can identify that field as an obstacle in the map, which the drone will not enter the prohibited field. The second method is using the obstacle avoidance system based on the radar, which I mentioned it in previous slides. And the drone detects the obstacle and change its route immediately. This picture shows a drone which is overing the power tower obstacle. Now, we want to list advantages of spraying drones. Usually, pests should be sprayed in a limited time window, otherwise it will cause too many damages to plant products. So the first advantage which I want to describe it for you is the speed of spraying drone. One of the most important parameter in spraying pests is the speed of spraying. The high moving speed of the drone makes spraying 1 hectare in only 8 to 10 minutes possible. It means these drones can spray 25 to 50, and in some cases, some of my friends sprays 90 hectares in one day, depending on the shape of the farm, depending on your spraying drone, depending on your spraying drone's tank volume, and so on. Some other parameters, but this technology can do it. The second advantage is water usage. In this, it is used 200 to 500 liters of water per each hectare in the conventional spraying methods. However, spraying drones use only 10 liters per hectare. It means 1/20 water usage. In these days, it is very important to use less water. The third one is pests usage. Using fewer pests is another advantage of spraying by agricultural drones, although it is common to use 10 liter, for example, some liters per hectare for most pesticides. For spraying some pesticides, it is used dosage per hectare. In such cases, using pesticides will decrease greatly. On the other hand, in cases with using liters per hectare in pesticide spraying, to ensure adequate spraying on the field, usually users add more pesticides to the spraying solution. For example, if a 1 liter pesticide is adequate, the user adds 2 or 3 liters pesticide to the spraying solution in the conventional method. In the modern technology of spraying drone, the exact prescribed amount of pesticide will be sprayed on the field and the plant leaves. This leads to using up to 30% less pesticides. So the first one is health. Usually, in the conventional method, health. Usually, in the conventional method, users need to enter the field physically to spray crops or trees. Agricultural pesticides are chemical material and have side effects. Based on experiences, the conventional spraying method users show symptoms like itching, redness of eyes, and diarrhea a few days after spraying the field, since drone pilots control the drone from the outside of the farm. In the modern method, the side effects will minimize. This feature is one of the most important benefits of using agricultural spraying drones. You can see in this picture the distance between the user and the drone, and the spraying machine is very far. In some cases, in some routes, the distance will be up to 1 kilometer, or in some cases up to 3 kilometers. And the pests will not be in the contact with the user. The fifth one is field coverage. Drones spray intelligently. In the first step, the pilot should map the field and upload it to the drone. Then the drone sprays the field based on the map truly based on the generated routes. You can see the generated routes in this picture. When the drone tank becomes empty or the operation stops for any other reasons, for example, the battery and so on, the drone saves the last spray point. You can see the blue icon in this picture, and it will come back straight to the saved point, this blue point, in the next flight and restart the operation. All of these happens thanks to the GPS system. Many of these drones uses RTK GPS system, which can fly with high precision. Yeah. The sixth one is uniform spraying. Drones execute the spraying operation uniformly on the field because the nozzles have equal distance from each other, and also spraying is done automatically. Maintaining a constant altitude using the altitude meter sensors help uniformly of the spraying. The flow rate of the spraying drone's pump depends on velocity of the drone, spraying width, and the desired liquid volume per hectare. For example, you want to spray 10 liters per hectare. Sometimes you want to spray 20 liters per hectare, and it depends on your decision. The liquid flow can be calculated from this equation. You can see it here from this equation, where F is the liquid flow rate in liter per second. The V is the drone's velocity in meter per second. The W is spraying width in meter. The A is the desired liquid volume, which and L is this desired liquid volume should be sprayed on 1 hectare in liter per hectare. Okay, you can see in these pictures a drone survey a field on these routes. This is the route spacing or spraying width, and the drone moves with the drone's velocity. When the drone moves with high velocity, the flow rate will be upper and will be higher than the average. And when the drone, for example, at the end of the routes, want to stop and change its round, the flow rate will be slowed down. The seventh advantage is flying in muddy fields. In spraying crops with a high need for water, like rice, or in the situation after raining, or in the case of flood, the only usable instrument for implementing of a spraying job is drones. The eighth advantage is spraying at night. Intelligent mapping and autonomous flight allow the drone to do the operation using GPS in the lack of light night. This helps the farmer, especially in hot seasons and warm climates. You can see these are some options. Sometimes you should spray at night, sometimes you should not spray at night, but it's an option. Sometimes you need a system to spray at night. The ninth is airstream turbulence effect. Airstream turbulence from above and high-speed centrifugal force generate micron-level droplets. Micron-level pesticide droplets evenly adhere to both the front and back surfaces of the crop leaves. This increases spraying efficiency. The last but not the least is soil compaction and plant crushing. Soil compaction is an important component of land degradation syndrome, which is an issue for soil management throughout the world. Soil compaction happens with commuting of agricultural machinery usually. Also, when you enter the field using heavy machines like tractor, entering the field may reduce the harvesting product up to 25% based on researches. In this picture, you can see that there is not any contact between the spraying drone and the crop field during the spraying operation. Now, we want to list 3 advantages of spraying drones. The 3 disadvantages of spraying drones. Although there are some drones which uses fuel or hydrogen as the power supplier, most spraying drones use electrical power to fly. Why? Most of you know that because the electrical drone have more simple mechanisms. Batteries are a limited power source, and the electrical energy consumption rate has a negative relation with weight. Besides the limited energy, batteries are expensive and have limited life cycle, and usually needs to replace after about 250 or 300 sometimes recharge times. On the other hand, batteries are sensitive and should maintain in a specific situation. For example, they should you should keep them in a limited temperature interval, or for example, you should keep them in a specific percentage of the battery. For example, you should keep them in about 50% if you want to keep them in a storage for and you don't like to use them for more than 3 days. They are so sensitive, you know, most of them, you know. The second disadvantage is liquid tank volume. In seminal type of spraying drones, which were released to the market, the liquid tank have only 5 and 10 liters volume tanks. These versions, with even using high endurance batteries, were only capable of spraying only 1 hectare at most. Recently, some companies have tried to produce spraying drones with high liquid tank volume, including 20 liters and 30 liters liquid tanks. However, the need for high liquid tank volume spraying drones is felt. The last one is the cost. Cost is another disadvantage of spraying drones. Agricultural sprayings are more expensive in comparison with some traditional spraying tools, and we should research more and increase their quality and decrease their costs. Spraying drones have multiple advantages and some disadvantages. In conclusion, it is highly recommended to use this modern spraying method, agricultural spraying drones, instead of traditional method. Not always, but when their advantages make it better solution to achieve more productivity, and it is suggested that other researchers work on improving battery function and smart spraying crops, in which the drone sprays only on infected parts of the field based on multispectral mapping systems. As I mentioned in I think first slides of in the above, some types of these drones are launched in the market, but it is a field that we researchers can focus on it and find better solution for spraying smart and use less pests on the crops. Finally, I want to thanks to Sharif Agrobot, an agricultural robotic company which has been supported us in this research. Thank you very much. I'm waiting for your questions. If there is any question, I can answer you. Thank you very much.
Amim, can you hear me?
Hello.
Hello, Amim. So thank you very much for your talk.
Can you hear me?
Yes, I can hear you really well. So thank you very much for your talk. Thank you very much for your presentation.
Thank you very much.
We have some questions here from the audience, and the first one is, which is the lifetime of the drones usually?
I can answer to this question two answers. The first one is the lifetime of the drones, and the second one is the lifetime of batteries. The lifetime of the drones is based on your usage. If you maintain them each season and overhaul them and behave to them in standard, you can use them for 2 to 5 years, but their batteries have a limited lifetime. The limited lifetime of the batteries is about 300 to 500 cycles. If you use them in a standard method, you can fly with them for about 300 flight in a standard, and if you can use them better, for example, keep them in a good temperature, keep them in a good moisture and some other conditions, you can use them for about 500 cycles. It depends on your usage. And the last one is that keep safe them from collision. If you keep your drone from collision or crash, we usually use this term, during the operations, you can use them for about up to 5 years. And after 5 years, I can tell you that you can use a better and very newer drones and technologies.
Okay, Amin, thank you very much for your answer. Amin, which is the efficiency of spraying in cultivars with abundant canopy, where only highly exposed leaves are in contact with the chemical that you're spraying? I mean, it's the same to spraying over a sugarcane cultivar, for instance, against an orange field or a strawberry field.
Now, if you use them in, for example, sugarcane or rice or wheat fields, now they can do your operation better, but new versions of these drones can spray in a spot mode. It means that it can stop on the top of the canopy of the tree and spray on that tree, and stop spraying and move to the next tree, and then stop again and spray on that tree. But not all of these drones can do these operations. Some of newer version of these drones can do it.
Okay.
Yeah, and I can, I can say another thing that based on our experiences in wheat fields, we could increase the efficiency about doubles by spraying on the fields, on the wheat fields, by drones in comparison with the
Okay, so this leads me to a second question for you. So it's the same from the efficiency point of view to use this kind of drones for spraying fertilizers against agrochemicals, against some diseases, for instance. So they are meant to use different kind of chemicals for different purposes, or what should we have into
no
to use properly these kind of tools?
No, we use the same chemicals and the same fertilizers in comparison to conventional method.
Okay.
Exactly. If, for example, if you should spray 1 liter of one fertilizer in 1 hectare with a tractor, we also spray 1 liter on a hectare with our drone, but in the tractor, your solution is 1 liter of the fertilizer in 200 or 300 water. Here we use only 10 water to solute them.
Thank you very much, Amim. And finally, we have one last question from the audience. So, Manuel, So in places where it rains constantly, this technology has many disadvantages, aren't they?
Of course. Of course, yeah, but in that situation, many other solutions are also have many disadvantages because the weather is wet and always the leaves are wet, and maybe you should use the pests in the irrigation in that situation. But many times, for example, you cannot fight with the for example, you cannot fight with that things with irrigation. Also, after the rain, you can only use the drone because the ground is muddy and the tractor cannot enter to the field, but the drone can enter to the field because there is not any contact between the instrument and the ground. Maybe, for example, in our country, the north part of our country is usually rainy, and they plant rice usually, and now using the drone in that part of our country is very common.
Okay, I mean, and finally, if it's possible to use different dose in a specific terrain, because when you are doing precision agriculture, you know that you have some differences in the same area. So it is possible to using the same drone to use different concentration or different dose for certain spots in the cultivar.
Of course, it means smart smart spraying. Some new version of these drones have this option that based on NDVI maps, you can spray on some parts of the field and not spray or spray little on some other part of the field. Yeah, it is possible, but it's very new in the market and also in the researches. Now, also we are working on this research, and we hope we can launch some new technologies based on this technology, based on these maps. Because for your question, we need some spots or some areas that should spray more.
Yes.
And we should find that spots or that spaces, that fields, based on some other technologies. That means, for example, multispectral drones or multispectral cameras. Yeah.
Amin, thank you very much. I learned a lot about drones today. So thanks a lot for your participation, and good luck with your doctoral studies in Iran.
Thank you very much. Thank you.
I have some good friends there.
Very good, very good. I hope I can be a new friend for you.
Okay, of course,
from now.
of course, Amin. Thank you very much for your presentation. It was really interesting.
Thank you very much. Thank you very much for this very good environment for this conference.
Thank you very much, Amin. So let's move on to next speaker, who is Edgar Correa. So Edgar Correa is an automation engineer. He has currently a master's degree at Pontificia Universidad Javeriana, and he's working under the Project Alliance in OMICAS. He's interested and oriented towards developing algorithms based on artificial intelligence techniques to analyze multispectral images, allowing the estimation of crops variables such as biomass, chlorophyll, nitrogen, and water stress, as well as the development of algorithms for the reconstruction of the plant architecture through the data fusion of multispectral sensors and phenotypic cameras, resulting in 4D mapping models for crops, cultivars, and plants. So welcome, Edgar. So we're looking forward to hearing you.
Good morning. I'm Edgar Correa, and I'm going to introduce you our research titled EFCATS, Annual Multispectral Image Segmentation Methods Applied to Precision Agriculture. This work was developed together with research Francisco Calderon and Julian Colorado, and we want to thanks to OMICAS staff, especially to SIAD, by giving us the dataset of image to do this work. The structure of this session starts with the motivation, in which we introduce the importance to use segmentation algorithms. In the contextualization, we talk about different approach or methodologies developed in the state of the art to generate a segmentation image methodology. In stage 3, we start with the core of the presentation, that is a EFCATS segmentation. Finally, the result and conclusion. The motivation to do a segmentation is because there is an image processing tool to evaluate the trails of crops. Usually, some research has been working with a multispectral area imagery. In this figure, we can see the sensor. Our sensor for this research is a multispectral camera that is characterized by integrate 5 sensors. The first 4 is a single channel sensor, red, green, red edge, and infrared, and 5 is an RGB sensor. Okay. The extension of the feature of the RLAN canopy feature is associated with physical-chemical variables. This affirmation is identified in a state-of-the-art, especially in this reference. We can observe the information that generates each channel from the rice crop. In this case, it's important the information related with the infrared channel. Okay, the motivation to do this is because we can identify the characteristics like the nutrient deficiency and evaluate the crop yield performance related with accumulated biomass. This information is the case by a lot of research in this area. To generate a contextualization, we can present these methodologies or this approach to generate an segmentation image. The first and the most simple is image thresholding, clustering, edge detection, and machine learning applied to these tags. It's important to this segmentation family, Magic Wand, IntelliSizor, GrabCut, and GrabCut. A lot of these have the same characteristic, that is interactive and based in an optimization process. Okay, depend of the result or the output of each algorithm, we can identify by one of these 2 things. If generate a hard segmentation that consists in a binary mask, one associated with a foreground and other and is associated with a foreground. The other option is to generate a sub-segmentation that is a mask related with a level of distribution. This distribution is associated with a probability to be part in a foreground group or the background. Okay, GFCATS is our proposed technique or methodology to generate a segmentation image. and consists in a formal approach to of interactive segmentation family. In this case, we use like a reference the graph code because it's the last of all of these developed. However, a lot of these has an have an related relation between together. This characteristic of this optimization, together with other two stages, confirm the novelty methodology for segmentation image. This is the structure of the segmentation methodology. The point one is associated with a acquisition image. In this case, the perspective information is so important. In stage two, we can observe the preprocessing of this image. In this case, it's important first to align the image because like our sensor have the different sensor in the different position. If we reconstruct this image, we observe an disbalance between each channel. After the aligned this each channel, we generate another resize to standardize the image. After the result of this stage is a image, a standard image with expected information to evaluate the FCAT score. This is the stage 2, 3, and 4. The first one consists in a binary classification and has two parts. The first is a Monte Carlo sample, and after consists in generating a cluster. In this case, we use a K-means algorithm. The result of this stage is to mask the first one associated with a foreground, and the last one is associated with a background. This is the input to optimization stages. Like I said, this is really associated with a graph code methodology, and the result is a binary mask. This result we can improvement through a guide filter. The input for the guide filter is this binary mask, and the image, the alignment image initial. Okay, the result of this guide filter is a soft mask, and if we want to compare with other techniques of the state of the art, we need to generate a binary mask. For this, we use an adapted threshold, but in the state of the art, there are other algorithms or other strategies to do this. In this case, was adaptive threshold. Okay, the first Monte Carlo sample consists in use, in this case, 20% of samples. Each sample is associated with a pixel, information of color pixel. The characteristic important is use a uniform distribution random over all of image. The result we can see in this slide. At the left, in A, we can observe a mask associated with a foreground, and B, we can observe an image associated with a background. At the right, we can observe the two clusters in a space of each band, each channel of the camera. The color of the cluster are associated with the infrared information. To evaluate different, to observe different clusters, we grab this with different size of sampling space. The more little is a ground cluster that contain a less level of infrared information, and the more bigger size of the sampling space is associated with the vegetation that is related with more content of infrared intensity. Okay, after this, We use the result of this stage to generate initial leveling for graph code optimization. This consists in a Gaussian mixture model to use to modeling the background and foreground. What happened here? The Gaussian mixture model learns and create a pixel distribution, create a graph. The node is the graph associated with the pixels. The weight of the of edge connecting the pixels from source node to the end node. These connect this associated with the probability of each pixel. Finally, after this, the pixel distribution generates a min-cut algorithm, use a min-cut algorithm to segment the graph. This do with a cost function like a sum of weight of the edge. With the result, we use or integrate an get filter refinement stage. This is based in a bilateral filter and consists in optimizing a quadratic function that directly impose some restriction on the unknown output. The input for this stage is a image, multispectral image alignment, and a binary mask generated with a optimization graph code. The solution is obtained by solving a dispersion matrix with information from guided image. The output of each pixel is weighted average of the neighbor pixels. These weights depend on the intensity and color similarities of the guided image. This is powerful by this approach. Okay, the result to generate an experiment we start with an generating run through. This is a manual process, and we use a software of image processing like Photoshop. This is the result of the run through mask, like a reference, and the result is evaluated related to thresholding, like a first algorithm identifying the state of the art. This uses the information of the histogram. The meaning is to identify the range in which the vegetation are set and generate this type of mask. This is the result in a standard image. However, in more complexity image, this approach is so back. The Camins use the previous meaning explained to EFCATs, use a 20% of the pixels to generate a characterization of the clusters, and with this information, the centroid and a maximum distance, we evaluate a lot of this image, other 18% of the image, to generate a complete segmentation for categorization to generate this mask. After, with graph code, we generate with a manual mask, manual initial interactive, and this is the results. And finally, the EFCATs, like I mentioned in a structure, this is the result. At the right, we can observe the result related to binarization of the EFCAT result in order to generate a binary mask to contrast with the previous explained show. To continue with the experiment, we use different image topologies. The first, at the left, is the image that contains some elements. We can observe the vegetation and a ground. And in addition, we can identify water and other elements like this that is bounded inside a orange oval. In the center, we can observe an image with light variation. At the right, we can observe a variation in vegetation associated with a stage of the crop, depending if it is ripening, vegetative, or reproductive. There are different topologies associated with a color, especially, and infrared information that contain the image. Okay, this is the ground truth generating, and this is the results. We can evaluate it or compare these four techniques: thresholding, K-means, graph-cut, and EF-cuts. And we compare a lot of this with these 5 metrics: evaluation metrics, true and negative net rate, true positive rate, true negative rate, Matthews coefficient, accuracy, and F1 score. And at the right, we can observe a box plot in which we can observe the performance of each one. It's important to mention that there are a lot of atypical points. This is associated with a complexity image you set, basically. Okay, it's important to mention that more details about these evaluation metrics and application of this EF-cuts approach we can find in this publication. Okay. To conclude, we can start with a pre-processing stage of the experiment. In this case, it was important to keep in mind the importance to align each channel. If we don't do this process in a good way, we can generate a noise and obtain a worse result. At the right image, we can observe the correct alignment of the image. Okay. In general, EF-cuts can operate in RGB standard. This important in this case is important to mention that the importance to use an hyperspectral image. In this figure, we can observe at the left the cluster generated by the 4 channels, especially the information, the multispectral information. With this cluster, we can obtain better results in contrast or related with a cluster associated with only 3 channels, 2 of visible spectrum, and only 1 associated with a hyperspectral. The better result is associated with a better comprehension of the clustering, in this case, to EF-cuts. Other important points is that generate this automatic approach that associated with a binary classification is novelty and useful because when we work with this type of projects, we have a lot of image and it's tedious and it's difficult to generate a same manually segmentation, initial segmentation in related to conventional family of algorithms that generate this segmentation based in optimization. Okay, for the result we use 4,400 samples for each techniques. The best result is the EF-cuts, mainly because it's an automatic graph-cut to generate the reference algorithm, generate a good result. However, the initial convergence is manual and this is tedious and generate a late time. Okay. Finally, to generate a result, the threshold, like a reference, present a good result in F1 score metric. This is associated with mainly with true positive rate, but not necessarily with a true negative rate. This is the disadvantage for these techniques. In contrast to K-means that in true positive rate is very low, and in true negative rate is high. What happened with the FCAS cuts? That in addition to be automatic, generating a good result between true positive rate and a negative rate that is disabled. Thanks for your
So Edgar, thank you very much for your presentation.
Okay, thanks to you for attention.
Here we have some questions from the audience, and also have a couple of questions, boring questions, so be prepared.
Okay.
So can be these algorithms implemented in different crops? Or what should be taken into account if you want to translate this kind of algorithms from rice, for instance, to sugarcane?
Okay, in this moment we use a rice crop and some image especially to develop the algorithm or technique. What happens if we want to use other type of image? We need to characterize the topology of image, especially what are the elements in the scene, and generate the cluster associated with the important to use an hyperspectral information to characterize the vegetation that is the most important in this case. Basically this.
Okay, Edgar. Finally, which is the correlation of biomass estimation when you use your approach versus on-field or lab approaches? Is a high correlation, or still you have to improve your algorithm to fit the field?
There are an agreed correlation between information. The important is to take the information, like biomass, nitrogen, what this information is found with instrumentation in a field. In this case, we don't, in this investigation, when this paper, we don't talk about this because the core is the segmentation. However, it has the potential to generate the correlation between a lot of this information.
Okay, Edgar. So some couple of questions for the audience. So this is Oscar. So Oscar asks, si el análisis que hiciste se hizo sobre una imagen o sobre un mapa ortomosaico de imágenes, y a qué altura se tomaron las imágenes, y en qué etapa de cultivo, y cuál fue lo que te pregunté, la correlación con la biomasa.
Okay, we use some image separately. The important for our experiment is use a different topology of image. In this case, we use the second stage of the rice. I don't remember the name. The altitude, I don't remember what is this. But this information is we can find in a data set of the image. We can find this in a link. I need to review this information, though I don't know this in this moment. The orthomosaic, no, we don't develop the orthomosaic with image. We only use 4 images with different topology.
And Edgar, do you think that finally these kind of approaches, the multispectral images, can replace the daily walks or the weekly walks that the person who are in charge of the cultivars do normally to really know what is happening with the cultivars? Or
I don't know the question. I don't understand the question.
Because you have we have the traditional approaches to estimate biomass. So for instance, we have the workers that are working on field, and on daily basis, they have to check the cultivar for different phenotypic measurements. And the question is if these kind of approaches can replace totally, let's say, the human perspective that we are having for years in order to really follow what is happening with the cultivars.
First we identify that is an invasive methodology, and this is developing some part of the developed crop. With this approach, we can do, like I said, unattended, generate our mosaic of a lot of crop and evaluate what part of the image in general, or mosaic, is associated with vegetation, and evaluate what happened with the evolution of the crop in the time. This is the potential of this approach. The multispectral information has the potential to do this work in a better way.
Okay, there. So, from a meme, could you describe the benefits of using drones of multispectral images in comparison to satellites?
The potential of doing and characterize the crop in a non-invasive method and in different type of the crop. Basically, we can characterize the crop in every moment with an approach that is not invasive. Basically, this is the answer. The problem is to generate a transfer with a farmer that not necessarily to know the knowledge about this type of technology. The work or the task is related to how we can to generate different roles in this farmer or in this farmer methodology or structure to generate crops, process crop.
Okay, thank you very much, Edgar, for your contribution. Thanks a lot for participating. Thanks a lot for your time and for your talk.
Thanks to you and for the attention. Bye.
Thank you, Edgar. So now if you want, you can visit some posters. So I'm going to share my screen. So I post on the chat the address where you can go for the posters. So still, if you have time, you can visit some posters. We have really nice and really interesting contributions made in posters. So if you have some time, you can navigate through this webpage and you can visit a specific poster that you want, and you can have a specific information. So in this way, it's possible to unload the poster if you want. And also, if you want, you can have a direct chat with some of the authors of the posters. And finally, so I want to thank to the all organization committee for this amazing 5 days of symposium. And also I want to thank to all the speakers and to all the contributors with the symposium. I hope to see you again the next year or in a couple of years when we are finally presenting all the results from the program. So we keep in motion and we keep motivated of doing some nice science that I'm convinced that we are able to change the perspective, not only from the region point of view and from the region perspective, but also from the national perspective and international perspective. So thanks to everyone for dedicated some time and for participating in the Congress. And see you hopefully the next year in a couple of years. So thank you everyone for your participation.
Thank you, Mauricio. Thank you, everyone. Thank you. Goodbye.
Thank you, everyone. And we'll see you next year.
See you, Andres, next year.
Take care.
Thank you very
I'll
much.
see you.
Thank you very much.
No, thank you, everyone. It was a very, very interesting symposium, and we look forward to more great work coming up, and hopefully some new collaborations that would come out of this interaction. Thank you. Take care, and keep yourselves and your families safe. And until next year, thank you very much to all panelists and all the symposium presenters.
Yeah.
Thank you very much.
Manuel Góngora is asking for proceedings, and the answer is yes. We actually will have some proceedings in the IEEE database.
Indeed, and please keep. You'll be posted. I mean, we'll post all the information updates on our webpage. The webpage is. I'll put it in the chat. OMICAS.co. And we'll keep everyone posted, and hopefully we'll send out a small survey just to make sure that we can optimize the future sessions of this symposium in a way that keeps everybody in the loop. Thank you very much.
Thank you, guys.
Take care. Okay. Take care.